And sure enough, it's the darkest of the satellites. That's sort of poetic justice that it turns out that way.
And that was known when they were named?
No. But nature was cooperative. Features keep showing up, and there are bright and dark spots. And some of our younger people are very tempted. They've looked at pictures of the Jupiter satellites and the Saturn satellites and the Mars and the Venus, and they say, aha, a ray crater. And we look at it, and they say, spectacular rays, and there's little tiny fuzzy lines. So we say, later we'll see those better. The thing that's fascinating is Miranda. Just a couple days ago, we weren't even sure it was round.
Really?
Well, the pictures looked sort of oblong. We said, well, it's really round. That's going to come in. And sure enough, it turns out to be spherical the way it should be. And then we saw a spot. And then they said, well, this is going to be like Mimas. It had such an enormous impact crater, it may have broken the satellite apart. Well, today we saw that feature, and it looks sort of square. It looks like sort of a square hole. And so we're not quite sure what that's going to turn out to be. But we'll see it 40 times better in just the next day. So nobody wants to say, I know what that hole in the ground is.
Not when within a couple of days it's all going to be revealed at that much resolution. Hal, thank you very much. Though Uranus was discovered more than 200 years ago, that's considered a recent discovery. All the other planets, except Neptune and Pluto, were visible and known to the ancients. It took a musician and an amateur astronomer using a telescope to find Uranus. His name was William Herschel, and George Fenneman talked with scientist Gary Hunt about him.
Gary, I understand that Uranus is the first planet discovered using modern technology. All the other planets were discovered by ancient man. Why don't we talk about the man who discovered Uranus?
Yes, he really was one of the greatest, should we say, amateur astronomers of all time. Hanoverian, born in Germany, a musician, who decided he wanted to come to England, and having made one visit one year, he came the following year and joined orchestras in the town of Richmond in Yorkshire in northern England. And then finally he moved to Bath, which is one of the spa towns discovered by the Romans, which was a major centre of entertainment and activity in Britain at that time. And he set up his work, he carried on his orchestral activities, teaching music, and as a hobby, his work in astronomy.
What year was this? 17?
This is in the 1750s. He started to move to Bath, and he became very active. And how he got really into astronomy was one night he was out in the street, King Street in Bath, observing the moon. And a gentleman tapped him on the shoulder, one Dr. Watson, who was a very distinguished British scientist, said, "Can I observe the moon through your telescope?" And they became very close friends, and Watson introduced him to the Bath Literary Society, which was the local organization where people came to discuss scientific and cultural activities.
And then from this, he built his own...
He brought his own telescope. He would entertain people to dinner. He could perhaps invite you and I to dinner one night. And after dinner, he would say, well, come and help me with some astronomy. Come and grind some mirrors with me. He'd have mirror grinding parties. And he carried on his astronomy, cataloguing the stars in the sky. And then one night in March of 1781, he observed one particular object and saw it on 3 consecutive nights. Then on the 13th of March, he was convinced it was the same object, which he thought was a comet. And he then took these observations, wrote the paper, which Dr. Watson presented to both the Literary Society and later in 1781 to the Royal Society, when he then became quite convinced it wasn't a comet, but in fact a planet.
Well, did he discover this ahead of everybody else because he had these parties at his house? He built a better telescope? Why was he able to see it?
He had an extremely good telescope. And in fact, later on, as he became more renowned, in fact, the king heard about him, this distinguished amateur who was doing excellent work, and the king summoned him to London. So he came with a 7-foot telescope, star catalogues, and everything else he discovered for an audience with the king. And before the king would really give him any patronage, he said, well, you must get the Astronomer Royal to check your telescope. And they were convinced that his telescope was far better than the professionals that they were using. And in fact, as a result of this, George III, who had previously been rather more occupied with the battles of his colonial states in America and other issues before really worrying about Herschel, decided that he would actually support Herschel in his work and gave him a civil pension of £200 a year, which in those days wasn't a bad sum of money. And also the Astronomer Royal, the leading professional astronomer, was only getting £300 a year. So he wasn't doing very badly. But one of the things he had to do as a consequence of royal patronage was in fact to entertain the people of the court. the king, the queen, the princesses, and so on, with astronomy and what was in the night sky with the aid of his telescope at Windsor.
Fascinating. Thank you, Gary. I'm George Fenneman.
Light has always been our key to learning about the heavens. That's still true today, even though many of our modern instruments can see light invisible to us. One instrument on Voyager 2 will measure distant starlight as it passes through the rings of Uranus. That measurement is called a star occultation, and Lonnie Lane is here to tell us about it. What's the instrument you use for that, brother?
Called a photopolarimeter.
It's not the camera.
No, it's not a camera. It's a very simple device in principle and really in practice. It has a light sensing element that can sense light changes in light very quickly, and that data is then digitized and sent to the ground.
So you get very, very rapid readings.
Very rapid
so
readings.
See changes in a hurry.
Correct. And so if a ring particle or rock or something were to occult, that is, stop the starlight, that changes the signal, and we detect that change. And you sample very, very rapidly and build up a high precision but very narrow trace across a ring or any other material.
So can you always find a convenient star nicely located? But
Oh, no. At Saturn, we were lucky. We had a few very nice bright ones. At Uranus, there was a real dearth of stars in the sky. We had very few.
I think we have an animation of how this whole thing worked. The thing you would have seen if you were on the spacecraft going past Saturn and then the one we're going to do past Uranus. Why don't we run that tape? Here we go right now. And there's a star, I guess, blinking across right in the middle of the shadow of Saturn.
That's right.
There's a star blinking on and off.
And the little trace on the bottom is the
I see.
apparent light.
The graph on the bottom is what your
light.
data would look like.
That's right. That's the light that's going through the various rings. There's Cassini division, where it's relatively clear, and then the A ring that was thicker. Light level drops.
And now we're going to
Right.
watch one go past. Which is
Right
this
there.
one?
This is Cygnus Sagittarius. It's an ultraviolet star, relatively bright, and it clips through the outer two rings, and a long, thin cord then goes across and coming back out again. The unique thing about this particular occultation is it doesn't go across all the rings, but very high spatial resolution, quite unique and unattainable on the ground or in Earth orbit.
And this other one that's coming up now?
That will be Beta Persei, and that makes a cut through the entire ring system.
I don't think we picked that one up on the tape. The information you got from Saturn revealed an enormously complex structure of the rings there.
And extremely dynamic and maybe quite temporal. That is changing its environment over a few years to maybe even a few months. In fact, there was a radio occultation on Voyager 1, and we found regions in the rings, in the C ring, one of the inner major rings of Saturn, that had changed drastically between the time of the radio occultation 10 months earlier and then the stellar occultation from Voyager 2.
Do you anticipate anything like that in Uranus, or do you have any way of telling this?
Well, the ground has done a very good job in stellar occultations because the geometry, that is the rings
how they were
facing
found,
upward.
weren't they?
Correct, by airplane and by ground studies. Then the rings seem to be, at least the scales the ground has seen them, less dynamic, but they all rotate as semi-rigid rotators, and they each have their own period and ellipse or near circular. And we will probe that at very high resolution because one of the major questions is, in the epsilon ring, the outer one, which is relatively thick and broad, does the material accordion as the ring gets wider at apoapsis, the distance part of the orbit, and then compress uniformly as it comes to the narrow part. And we're just lucky enough that the first occultation gets near to the narrow part, the periaps, and the second occultation will cut very close to the apoapse, or the distant part. And by comparing those two, we'll look and see, does the internal structure stay constant, which is what one theory requires, or is it jumbled in some way and then reforms? And that requires a whole new mechanism.
And also, similar questions may apply to the other smaller rings.
That's correct.
Lonnie, thank you very much.
Thank you.
We're receiving more than 200 images a day from Voyager 2. Now, that's considerably less than we got during the earlier encounters at Jupiter and Saturn. And there are two reasons for that: a far greater distance to Uranus and the constraints the engineers have placed on the spacecraft. Because of the distance to Uranus, it takes a picture 2 hours and 45 minutes to reach Earth, traveling at the speed of light. Those pictures continue to come in, and the scientists continue to pore over them. And Bill Griffith has more on that.
It's one of the largest satellites in the Uranian system. At 1,630 kilometers across, it's about half the size of our own moon. So far, Voyager's latest photos of Oberon have not really told scientists anything they didn't already know about it from their earthbound observations. What is known is that it's covered by a thin layer of water ice. But imaging scientist Bob Brown especially pointed out a group of dark spots on its surface.
One of the interesting things that we've seen in some of the latest images is this feature here, which has quite a dark center, and there's a bright area around this. Although the resolution is not extremely good right now, what we're thinking at this time is this is perhaps one of the first craters that we're going to see on Oberon. The other interesting feature that we see in this low-resolution photograph is that there is another feature here which may be a crater. It has a dark central area, and it has a fair amount of bright material which may have been thrown out when this crater was created. Probably what has happened is that when the impact occurred, water ice, which is the main constituent of the surfaces of most of the Uranian satellites, was thrown out, and that's what we see here.
The mystery satellite at this point is Umbriel, which looks like a giant golf ball. It measures roughly 1,000 kilometers across, and it's probably covered by a very thick layer of ice. But it is the darkest satellite in the Uranian system. It reflects only about 12% of the sunlight that hits it. So Dr. Brown says less is known about it.
Though we have known for a long time that Umbriel is composed of water ice, it is much darker than the rest of the large satellites, and therefore most of its surface must be covered with dark material. And we're beginning to see that what we have here is a very, very low contrast surface, although we are starting to see hints in this region, for instance, of a little bit of contrast. We may be seeing hints here of a rather large crater. Although this is pretty speculative at this point because we have very little information, you can see a brightening in this area and then darkening in this area. And this may be telling us that this will be the first impact crater that we see on the surface of Umbriel.
From the Image Processing Lab, I'm Bill Griffith.
Voyager 2's closest approach to Uranus is now a little more than 16 hours away. It occurs at 10 tomorrow morning, Pacific Standard Time. The 6 hours before and 2 hours after that will be the most crucial. That's when Voyager 2 will record its highest resolution pictures and other science data. Project scientist Ed Stone is with me again. Ed, what are your predictions, if you have any? Or what are your hopes if you don't have predictions?
Well, I have hopes that all of the things we have planned, in fact, execute exactly as we have them planned, because everything we've been doing to date has really been a prologue for the next 24 hours, because that is the primary scientific return will occur in the next 24 hours. Now, all of it won't come back tomorrow, because some of it is put on a tape recorder, but that is the period when, in fact, it's all recorded.
And will all of the instruments be used? I presume everything on there is going to be used.
Yes, every single instrument will be used. The instruments on the scan platform will be studying the planet at the highest resolution. They'll be studying the rings at the highest resolution and the satellites at the highest resolution. The other instruments, which sense the magnetosphere and the particles trapped in the magnetosphere and the waves, will finally be within the planetary magnetic field for the first time. And then we'll use the radio system on the spacecraft itself to probe the atmosphere and the rings via the occultation technique.
As we go behind it.
As we go behind.
From the point of view of Earth. We've talked earlier in the program about how much we've changed the spacecraft since it left Saturn before it got to Uranus. Have we made any changes since we got near Uranus based on what we've seen at Uranus?
Well, yes. In fact, one of the images that's coming down in the next 24 hours is an image of 1985 U1, which was just recently discovered, and we have reprogrammed one particular image from Miranda to that new satellite. And we're also doing some fine adjustments later this evening, which will tune up the pointing for the most critical observations at the time of closest approach.
What kind of adjustments are these?
Well, they're final pointing adjustments when we get the best possible information as to where the spacecraft is with respect to Miranda, which is our closest approach. And we put in the instructions in the computer so that it will, in fact, have our best targeting on Miranda.
That has to be done pretty much at the last minute because of the data still coming in as to where everything is.
That's right. I think the commands actually go up sometime like 1 o'clock this morning Pacific Standard Time.
Calling a little close.
Yes, it is.
And what do you anticipate anything particularly different in the fields around the hint of the magnetic field? Is that going to make a particular large difference between this measurement and those near Jupiter and Saturn?
Well, I think in any case the magnetic field is going to be different because it will be likely tipped on its side just like the planet. So we'll be going in from the pole of the magnetic field. There could be a very intensive radiation environment if some of our earlier indications are correct. And but on the other hand, we just have no idea. This is really a unique magnetosphere.
Also, I've heard that it's possible that we may be getting more indications of magnetic field once we get around behind the planet than we are from out in front of it.
Well, there may well be a magnetotail. One would expect that the solar wind, which essentially blows out from the sun, will deform the planetary field into a long tail-shaped structure. And as we go behind the planet, we will enter into and probe the tail region of the magnetic field.
The satellites, are there any others besides, any other new ones we're going to be looking at deliberately besides?
No, that's the only one that we'll be particularly trying to image.
But we'll be getting pictures of the rings and perhaps satellites in there, even though we don't even know they exist yet.
Yes, we'll be certainly looking for additional shepherding satellites.
Thank you very much, Ed. Well, today we've seen quite a bit of new information. We found some new satellites along the way. We have today some evidence for a magnetic field associated with the planet Uranus. We've seen a number of clouds moving in the upper atmosphere and haze around the South Pole, and the first hint of perhaps some sort of features, maybe even geologic formations, on the major moons. Tomorrow, closest approach day, a day during which we expect to gather more information about the planet Uranus and its satellites and its rings, more than in the 205 years since its discovery. Also, the day that Voyager 2's trajectory will be changed by Uranus gravity. As it swings around Uranus, and Voyager will be placed on a course to its next destination, the planet Neptune. It will reach Neptune August 24th, 1989, after traveling another 1.2 billion miles. I'm Al Hibbs of the Jet Propulsion Laboratory in Pasadena, California. We'll hope you'll join us tomorrow as we continue to watch Voyager 2 spacecraft's encounter with the planet Uranus.
Snowmobiling, and perhaps you'll just want to go out for a walk under the light of this wonderful, crisp and clear January moon. And while you're out there, you might want to take a look once again for the star pattern we talked about last week, Orion the Mighty Hunter. Easy to find even when the moon's full, because his stars are so incredibly bright. Simply go outside around 7 p.m. or so, look to the southeast, and there you'll easily spot 3 stars, equally spaced in a perfect row, which marks the belt of Orion. Directly above are 2 bright stars, which mark his shoulders, and directly below the belt are 2 bright stars, which mark his knees. Now, interestingly enough, for thousands of years, the majority of human cultures, although separated from each other geographically and culturally, have invariably seen this group of stars as a great heroic male figure. And there are absolutely marvelous legends about Orion, some of which we wouldn't dare talk about on television. But some of them are truly wonderful and show us how our ancestors used sky figures to pass on their history, their mythology, and even their moral lessons. The stars in the heavens were, as a matter of fact, a sort of a mythological library for most cultures. And long before man learned how to devise methods to write down his history and what he thought about the universe, he used star patterns, which seemed almost unchangeable, as a way to communicate and pass down what he felt was important. One story of Orion the Hunter, which I particularly like, was used as a moral lesson to teach youngsters about the consequences of boasting and bragging. In this story, Orion was said to be the son of the king of the sea, Neptune, and the sea nymph Eurale. Now, Orion was no ordinary mortal. Indeed, he was a walking giant with the strength of an Atlas and the handsome features of a matinee idol. And it was said that he was so tall that he could walk through the deepest water in the oceans without even getting his hair wet. And it was also said that Orion had no fear whatsoever of any animal, even the wild and ferocious lion. Indeed, one day Orion proudly boasted that not only was he not afraid of any of the creatures of the earth, but that he could exterminate them all if he wished, and that not one of Earth's creatures could dare do anything about it. Well, wouldn't you know, the wrong person heard about this braggadocio, and she was the goddess of the earth, Gaia. Now, she was so infuriated that she sent for one of her tiniest creatures to do Orion in. Orion didn't even see the tiny animal as it stung him in his heel. And as one might say today, he never knew what hit him. Orion collapsed mortally wounded, and even today, he and the creature that bit him are never ever seen in the heavens together. And who was that ancient killer of Orion, you ask? Why, Scorpius, the scorpion, of course. So, out under the stars with you to see the boastful giant, and until next time, be not proud nor vain, my friends, as you remember to keep looking up.
When you see Halley's Comet for the first time, we'd like to hear about it. Just drop us a line in care of this station. Star Hustler is brought to you by the Carl Zeiss Companies of North America. We're setting the standards with products for medicine, research, industry, and the quality-conscious consumer.
So it could sweep past Uranus and send back pictures today to excited scientists below. We have a full report from Jeffrey Kay of public station KCET, Los Angeles.
These scientists at California's Jet Propulsion Laboratory, JPL, are discovering more about Uranus than explorers like Christopher Columbus or Ferdinand Magellan ever learned about Earth.
Uranus is the most distant object from Earth ever visited by a man-made craft. Today at JPL, scientists treated the event with what one described as controlled pandemonium.
Yesterday I was showing you some lower resolution color images of the satellites. This now is our...
Pictures released today show details of the rings and moons of Uranus. Voyager 2 has found 9 new moons and a magnetic field around the third largest planet in the solar system. But much data remains to be analyzed. Chief Scientist Edward Stone said the best is yet to come from today's flight 50,000 miles over the clouds of Uranus.
Everything you've heard to date is a prologue to what is now happening, and the next few days we'll really have the discoveries that we've all been waiting for.
The ingenuity of hundreds of scientists and engineers sent and controlled Voyager 2 on its 8.5-year journey, 2 billion miles from Earth. In one day, today, researchers will gather more information about Uranus than they have collected since the planet was first discovered by British astronomer William Herschel in 1781.
And Herschel discovered Uranus. Yeah. Really, if you wanted to see Uranus, you had to go use his telescope. Herschel had the best telescope in the world. He was the only one that could see it. And yet today, because of modern communication, actually everybody can share in the discovery at the moment of discovery. I mean,
Chief Scientist Edward Stone supervised the experts from around the globe who planned Voyager 2's trip and who last month converged on the Jet Propulsion Lab to examine the findings.
Well, I can show you the first spectrum of the Uranus. It is average.
Rudy, can you hold it up so everybody...
Teams of scientists conducting a variety of experiments are busy scrutinizing the data Voyager is transmitting. The spacecraft has looped through the solar system, providing scientists with close-up studies of Jupiter in 1979, then Saturn in 1981. Saturn was to be Voyager's last encounter before hurtling beyond our solar system in the wake of its sister ship Voyager 1. But as Voyager 2 swung by Saturn, engineers managed to redirect it. Using Saturn's gravitational pull, they catapulted the craft towards Uranus. Project manager Richard Laser was responsible for making sure the craft's onboard computers received and obeyed the commands to alter course.
The spacecraft is so far away that radio transmissions, which travel at the speed of light, take 2 hours and 45 minutes to go from the Earth to the spacecraft, and another 2 hours and 45 minutes to come back. So when we send a command, we don't see the results of that command until 5.5 hours later.
Voyager 2 has been constantly receiving commands sent by 11 teams of scientists. They have been busy directing and redirecting the sensing devices on the 1,800-pound spacecraft in order to learn about the planets and their environments.
Number is ON0044.
This is mission control, in effect the Voyager 2 driver's seat. Here, the scientists' instructions for the spacecraft are communicated in a form Voyager will understand. Those commands are relayed through the Deep Space Network Control Center. This center sends information to one of 3 transmitting and receiving stations around the world, located in California, Spain, and Australia. As the Earth rotates, one will always be pointed at Voyager. The material received today came via the station at Canberra, Australia. The scientists studying this planet received increasing amounts of data each day as Voyager 2 approached Uranus. Today they hit the jackpot. 6 hours worth of information as Voyager passed in and out of the planet's orbit.
This kind of scientific experience is rather different than most, and that in the sense that every day you learn so much more than you knew the day before. Normally, you learn something and then you think about it and you maybe repeat the measurement 6 months, a year later. Here, you see something one day and you know tomorrow you're going to see it better. And the next day it's going to be better yet.
Because of the time delay in communications, scientists had to program Voyager's encounter activities way before today's event. As the spacecraft whizzed past Uranus at more than 40,000 miles an hour, there was no opportunity to make last-minute adjustments. By the time the first close-up picture of Uranus was being processed on Earth, Voyager was out of the planet's orbit. To the public, pictures are the most tangible souvenirs of the Voyager trip. But it's not just a matter of snapping pictures. Because there's so little light available on Uranus, the exposures had to be long ones. However, taking a picture of a moving object from a moving object generally results in a smeared image. Voyager engineers rose to the occasion.
And so one of the big challenges that we undertook was what we call the smear reduction campaign in the 3.5, 4 years between Saturn and Uranus. And we've done some truly amazing things with both keeping the spacecraft very steady and introducing a technique where we actually follow the target, follow the motion, like following the race car if you're taking a picture of the race car.
Taking the pictures is one thing, figuring out what they mean quite another. To interpret them, members of the imaging systems team huddle over video monitors. Scientist Richard Terrell watched the dots, splotches, and rings around Uranus grow bigger as the Voyager encounter approached.
The one thing we can expect during the encounter is we can expect to be surprised by something. We're always going to find something we had no idea was going to be there.
Richard Terrell's last surprise was this. He took the first picture of a solar system outside our own. Now he's preparing for more discoveries. 1 week ago, Terrell's excitement was evident as he manipulated his computer controls to examine the mysterious rings around Uranus.
Our expectation is we may even be finding moons within the known ring system. In other words, one of the questions we ask scientifically is what is causing the gaps between all these little rings? What's separating the rings? And one popular theory right now is that the rings are shepherded. That is, moons which orbit between the rings actually push the rings together and make them that narrow.
Today, Terrell said that thanks to some of the 6,000 photographs sent back by Voyager, his hunches were confirmed.
Oh, this is great. This is a moment of a lifetime for an astronomer.
Terrell and his team discovered 2 moons within the rings. They expect to find more as Voyager 2 continues its journey. The spacecraft is now flying behind Uranus, taking pictures as the sun shines through the rings. The expected backlit images should reveal the composition of the rings and atmosphere of Uranus.
And if anybody's been in say a movie theater And, you know, you look up at the screen and watch the movie, and you never notice any dust in the room. But if you turn around and look the other way at the movie projector, all of a sudden you notice all the dust and cigarette smoke and everything else in the room lights up in the light of the projector. Well, we believe the same thing will happen with any dust in the rings. It'll suddenly light up and become visible.
Although the pictures of Uranus received today are dramatic, the best close-ups should be released in the next day or two. The images already taken must travel through 2 billion miles of space before Earth-bound scientists subject them to complex processing techniques. Richard Terrell plans to spend hours and hours studying every dot and squiggle on those pictures. For this scientist, taking the mystery out of the stars and planets does not reduce their romantic qualities.
If you think about it, science fiction has always outpaced reality. I mean, in science fiction, they've thought of these beautiful, romantic, ice-covered worlds and all these things like this. But this is reality now we're talking about, and there are ice-covered worlds out there. There are worlds out there within our own backyard that even exceed the expectations of science fiction authors.
There will be plenty more data for Richard Terrell and his colleagues to analyze. Voyager 2 is heading for a 1989 rendezvous with Neptune before heading out beyond our solar system.
Satellite Titania. The photo was taken by Voyager 2 several hours ago as the spacecraft was 92,842 miles from Uranus. This is the NASA Science Report.
NASA Science Report is a special summary of events leading to the Voyager 2 spacecraft's encounter with the planet Uranus. The programs originate live from the facilities of the Jet Propulsion Laboratory in Pasadena, California, and are authorized by the National Aeronautics and Space Administration. The NASA Science Report, Voyager 2 at Uranus, is one of a series of public information programs designed to keep the public informed of space exploration.
Hello, I'm Al Hibbs at the Jet Propulsion Laboratory. We're watching NASA's Voyager 2 make its closest approach to the planet Uranus. This week, we're looking over the shoulders of Voyager scientists as they receive new information on Uranus and analyze it in its original form. We'll be discussing its significance, the mission's scientific goals, and what this encounter can teach us about our world and the universe. At 10 this morning, Pacific time, Voyager 2 passed closest to Uranus, within 50,600 miles of the cloud tops. During the 6 hours before closest approach, and the 2 hours afterward, Voyager 2 has been busier than at any time since it passed Saturn in 1981. In that period, it made its closest approach to the satellites in the rings. Then, Voyager swung behind Uranus, out of contact with the Earth, to conduct radio science experiments. Then, at 4:46 this evening, when the Voyager had, that was 2 hours and 45 minutes after Voyager 2 emerged from behind Uranus, we reestablished clear radio contact with it. It's been busy here at JPL since we talked to you yesterday, and with me to report on all the activity is Dr. Ed Stone, the Voyager project scientist. Ed, once again, I'll ask you, well, how are we doing? What have we learned in the last 24 hours?
Well, we've, first of all, mainly learned that the spacecraft is doing exactly what we'd hoped it would do, and that we are, in the next 24 to 48 hours, going to be seeing things that we've never seen before.
It's been remarkably reliable.
It has.
For this ancient, aging spacecraft.
That's right. Well, it's working better in many ways than it did at Saturn, so I think that's an important thing to keep in mind. But we did already manage to confirm that, indeed, there is a magnetic field. Directly by directly measuring it as we entered into the magnetic field.
This was with the magnetometer.
The magnetometer.
Seeing radio waves.
That's right, and also the other instruments which measure the trapped radiation also sense the edge of the magnetic field. So there's no question but what there is a sizable magnetic field. We still have to sort out what its real configuration is, and that's what's ahead for the next day or so.
How long will we be embedded in this magnetic region dominated by Uranus? Are we going to stay there quite a while?
Well, the current estimate is that we may be in it all through Saturday and Sunday, and perhaps leave late Sunday, early Monday. But again, those are only estimates at this time.
We've had pictures of the moons taken several hours ago, but of course our best pictures have been taken quite recently, and they're all stored. And when will we see those?
Well, those come back to Earth tomorrow afternoon, and I suspect that we will suddenly begin to understand some of the features which are quite puzzling, which are showing up in the lower resolution images.
And the other experiments that are looking at both the moons and at Uranus? We have spectrometers and so on. How are they doing?
Well, we did have a very successful stellar occultation, which means that we watched measured the amount of starlight as the star went behind the rings as viewed from the spacecraft, and that's going to provide us very high resolution information on exactly what the structure of the outer two rings of Uranus it really is.
That's the way those rings were discovered from Earth, wasn't it? By watching starlight getting blinked on and off as it went?
Exactly the same technique. From Earth, one is limited to resolving things which are about 3 kilometers, about 2 miles across. From the spacecraft, we can see things which are on the order of 50 feet across.
So we'll be able to see lots of structure in the rings. What's the chances of seeing something with such resolution we can actually measure the material in the ring?
I doubt
big things like Saturn, blocky things like Saturn.
I doubt we'll do that with the photopolarimeter, but the radio occultation experiment, which is going on right at this time, is the one where we actually transmit the radio through the rings from the spacecraft to Earth, and we observe how the ring material scatters the radio frequency. And by working the data analysis, one can interpret that scattering in terms of the size of particles which are in the rings.
The spectrometers have been looking at the surface of Uranus. Have we gotten any better idea of the structure of that atmosphere?
No, we do have some indication that the lower latitudes may be less hazy than the polar region, which is what we may have been seeing. So again, the images which have just recently been acquired and are being stored on the spacecraft may produce a rather different view of the Uranian atmosphere than we've seen from the pole.
We have, however, something of a temperature measurement.
Yes. Well, we do know that that the temperature is to first order exactly what we expect. And now the real question is if we can now resolve separately the temperature at the pole and the temperature at the equator. Again, that same data is currently being stored on the spacecraft so that we can make the temperature map.
Does it appear from these first numbers that the temperature is warmer at the pole, where the sun's been hitting on it for, what, 20 years?
I think that one would expect the temperature will be a bit warmer at the poles than at the equator, but we don't have an equatorial measurement yet.
Ah, I see. So we're still waiting to get that sidelong view. And I presume we'll also turn the spectrometers on the satellites.
Yes, although I think the main thing we'll do with the satellites is with the photopolarimeter, which will measure the amount of scattered sunlight, which tells us something about the texture of the material on the surface.
Thank you very much, Ed. Uranus, of course, was of interest to astronomers long before Voyager was launched. We knew it was accompanied by 5 satellites. And then in 1977, astronomers using an airborne observatory discovered this set of very narrow rings we've just been talking about. It was hard to explain why the rings were so narrow. Was it perhaps because they were shepherded by tiny satellites? Karen Long talked with Dr. Jeff Cuzzy during a search for those moons.
This is perhaps the first clear image of one of the most exciting new Voyager 2 discoveries at Uranus. 2 shepherding satellites at the planet's outer epsilon ring. It's a 15-second exposure taken some 4 million miles away. According to imaging team member Jeff Cuzzy, the satellites are moving at a rate of approximately 5 miles per second, performing some important gravitational work along the ring.
You can see by their configuration that they act like, it was suggested at Saturn, like sheepdogs or shepherds to confine this unruly flock of ring particles from spreading out in all directions.
Would there just be 2 within the realm of that outside ring?
Well, there may very well be more. As we looked at the images coming down, we all had suspicions of little blips and streaks. There could be other things. And this Uranus system could be very full of junk. For instance, you know that outside of the ring, the main of the ring system in the satellite area, there have been 7 new satellites discovered. And we anticipate finding maybe another 10 or so, within the rings themselves.
The Shepherd satellites are approximately 20 to 30 kilometers in diameter, only 1/2 to 1/3 the size of the newly discovered satellites outside the rings. Why is it the satellites appear long and slanted in the image?
It's slanted because of the motion of the satellite itself, which is about 5 miles per second around Uranus. You can see this star here is smeared less. That's just the motion of the spacecraft. So that's how we tell the difference between a star and a satellite. And the way we know where the stars are is by the navigation team on Voyager has done some very nice work on predicting the location of all the stars that are in each frame. And they can go and very exactly calculate where the camera's pointing and what star we're looking at. So we can actually compare, and measure, in fact, the velocity of the satellite in its orbit.
Voyager 2's cameras will take a closer look at the rings and their satellites toward close encounter.
We have another set of observations which has even higher resolution on the rings than these by another factor of 3 or 4. Okay, and they look something like this, where the camera frame is stepped across the rings in this sort of fashion. Now, unfortunately, because of time constraints, and everybody else wants to look at other things at this time too, we only have about half of the ring covered. That means we'll take this little patch of 6 and then do it again here, and again here, and again here, and again here.
So we may miss satellites in between.
Right, there are gaps. So it's a bet that you got to take. But if there are 10 or so satellites, then on the average we should be able to get 5.
Interesting, Jeff. It's now assumed that the satellites, rings, and their shepherd satellites were all created at the same time the planet was created. And as we further study these phenomena, we'll undoubtedly learn a great deal more about the formation of our entire solar system. At the Image Processing Lab, I'm Karen Long.
Since the beginning of Voyager 2's encounter with Uranus, we've discovered 9 additional moons orbiting the planet. In 205 years preceding the encounter, we were aware of only 5 Uranian moons. Now we know there are at least 14. Uranus satellites are different from our moon, as Uranus is different from the Earth. George Fenneman talked with Torrance Johnson about the Uranian moons.
Torrance, I understand that the Uranian satellites are very dark. They're supposed to be made of ices. Why would they be dark if they're made of ice?
Well, this is actually one of the things we're going to be looking for in the data that we get back. We know their surfaces are composed, at least partially, of water ice. We've seen the spectral signature of this from data from ground-based telescopes. But they're dark. They're not tremendously dark. They're still, on the average, say, twice or 3 times as bright as the Earth's moon surface is. But that's still dark if you consider that the pure ice ought to be have a very high reflectivity. Some of the other moons we've seen in other parts of the solar system have been very bright with ice. So we're pretty sure that the answer must be that the ice is mixed with darker material, rock or carbonaceous material of some sort.
Oh. What are the sizes of Uranus satellites?
They're sort of what you might call mid-range. The 2 big ones, Titania and Oberon, are about half the size of the Earth's moon. Then there are kind of 2 middle-sized ones, Ariel and Umbriel, which are, again, half again as small as that. And then there's the smallest one of the 5 satellites that were known before Voyager, Miranda, is only about 300 to 400 kilometers in diameter.
Who gives the names to satellites? These names are a little different than, aren't satellites usually named after Roman and Greek gods?
A lot of the earlier ones were, of course, these satellites were discovered a little bit later in history because they're further out. Herschel saw a few of them when he discovered the planet. Others were tracked later. Miranda was discovered in the 20th century, actually, by Gerard Kuiper. The names were historically given by the discoverers with the consent of the international community. There now exists an International Astronomical Union, which has a commission that approves names. So newly discovered satellites now go through quite a long process, actually, of having an international committee look at various possibilities for their names and give them. They usually try to take historical context and cultural context of the pre-existing names into account when they do that.
It seems to come from Shakespeare, though. These, at least some of those.
At least 3 of them are in Shakespeare. Umbriel, I believe, is in Pope's Rape of the Lock.
Well, I wouldn't know. How your study of satellites, how does that help us understand the Earth better?
Well, basically, we're looking at solid worlds, if you will. We're interested in looking at them not only as examples of pre-existing solar system material that formed around these bodies, but as individual worlds in their own right, how they evolved, how they tick, basically. And these things are made of different materials, have had different histories, so they represent what you might call experiments in planetology that we can't do here on Earth. So it helps our understanding of the basic fields of geochemistry and geophysics, the types of things we use to understand our own Earth.
Well, I appreciate your helping me understand a few things. It's been a pleasure talking to you. I'm George Fenneman.
And now, through the magic of live television, Torrance Johnson is with me here in the Blue Room. Torrance, What can we say about the satellites now that we're getting slowly but steadily more information?
Well, we're now past the point at which they're just sort of unresolved blobs. The pictures that we got back today started showing really not only individual character, but enough detail on the surfaces to give us a lot of enthusiasm and hope that the highest resolution pictures still to come will allow us really to understand the processes going on those surfaces, compare them among the satellites, and to look at them with respect to the other satellites in the solar system.
I'm sure that, that we have seen evidences of cratering on the surfaces by now.
Yes, as of yesterday, we had seen a lot of things that were splotches that looked a lot like the patterns that are formed by impact craters with bright rays on relatively darker surfaces. But in the data that came back late last night in real time and the data that came back today, we see enough of the craters at higher resolution on the terminator to be sure that we've got holes in the ground. The best pictures that are coming in now, or that came in a little bit later today, definitely show multiple craters on the surfaces and things that are not craters, just as we have seen at the...
oh, you have some evidence of formations then that are from internal...
There are some things that look definitely like they're, as we say, tectonic features, things associated with internal processes on the satellites. And, of course, we've only got them resolved in the more or less lowest resolution pictures of this sequence now, but the data that's on the tape recorder will, we hope, really reveal a lot to us.
Was this, in any sense, a surprise that they're awfully cold?
Well, we're, after Jupiter and Saturn, we are no longer surprised at being surprised. We should be surprised at small, cold objects having internal activity, but we've found many examples of Mother Nature figuring ways to do it as we've gone out into the solar system and explored. And one thing we don't know, that we'll have better answers for after we've looked at the highest resolution data, is what are the relative age sequences on these satellites? How do the crater densities, when we do the numbers, compare with the crater densities that we see in the other parts of the solar system, Saturnian satellites and the Jovian satellites, and between the satellites of Uranus themselves? We now know that there are those features there to look at. We suspect there are other things there which can also be dated and dealt with in a geological sequence, and we don't know what surprises that holds yet when we get the best data.
Are we going to have to presume that the cratering process is as intense near Uranus as it is near Saturn and Jupiter? Is there some reason to believe there's a variation through the solar system?
Well, that's one of the questions we have, that there are possible reasons for variation, but the best way to tell that type of thing is, in fact, to look at the satellite surfaces and compare. One of the things that's always intrigued us about the Uranian system, of course, is that it's tilted over on its side, suggesting that the satellites probably got themselves together after that tilting occurred. Now, when that tilting occurred, how long it took the satellites to form after that, with respect to the time scale of the bombardment of the other outer planet satellites, is one of the things we're interested to look at.
Thank you very much, Terence. We've received literally tens of thousands of pictures from the two Voyagers during the encounters with Jupiter, Saturn, and Uranus. It's a lot different from taking pictures of the family vacation with your pocket Instamatic. David Sparks is standing by in the Spaceflight Operations Facility here at JPL to tell us more about how we get those pictures back here from space.
It is decidedly different than standard photography, Al, although the results are pretty much the same. Good, clean pictures of the subject. Now, let me present the problem to you. You have a spacecraft which is about 2 billion miles away from Earth. How do you take pictures and, in a sense, develop them and then transmit them back home from a spacecraft that has, mind you, been traveling for 8.5 years? Well, the answer to how this is done is just a little bit complicated, but fortunately, Andy Collins, who is a member of the imaging team, shared some of his time with us.
Focus
Cleared some
using
of this
optical
up.
systems onto a selenium-sulfur Vidicon tube, where the charge pattern that results is scanned with an electron beam, converted into an analog signal, which is then digitized and used to modulate a radio signal directed towards the Earth. This signal is received by a sequence of antennas on the ground. It is reconverted back into digital data, stored and processed in computers to represent the scene.
That's easy for Andy Collins to say because he's a member of the Voyager imaging team. But what about putting all of that into terms that are just a little bit more familiar to most of us?
There are two cameras They have optical systems which aren't altogether unfamiliar to amateur astronomers and photographers. These optical systems focus the light from the target, from the planet or the satellite or the rings. They focus it onto a vacuum tube. It's a Vidicon tube that you see here. The Vidicon tube is used to change the pattern of light which falls on its front surface into a pattern of electronic charge. So from the Vidicon tube, we get an electrical signal where the size of the signal is proportional to the brightness in the original scene. These measurements are converted into numbers between 0 and 255 and are transmitted on the radio link between the spacecraft and the ground. So the picture actually resembles nothing more than a string of numbers that have been coded and transmitted to the ground the same way one computer might talk to another computer on a telephone line on the Earth. So when Voyager is really churning out photographs, we'll have on the order of 40 pictures strung out between Uranus and the Earth at any one time. There'll be a long, long line of numbers, about 2 billion miles long, and those will be the numbers to compose 40 images. And then the computers then take these numbers and use them to operate film recorders or television sets in which the brightness is proportional to the number that they're looking at. So a high number coming back indicates that that particular location in the image is going to be bright.
Take a look at the photograph on the upper left. The arrow points to a crater. On the upper right, there is a magnified image of the crater. And below, a matrix of numbers which represent the levels of brightness for each portion of the photograph. Zeros mean no light, and high numbers mean bright light. Voyager's radio system returns these numbers to the ground, where computers turn them back into pictures. Land-based telescopes seem incredibly sophisticated in what they have told us, so is it fair to assume that what you're going to measure is going to improve what we know about Uranus?
Through even the largest telescopes on the ground, Uranus is just barely more than a single point of light. So there's relatively little you can learn from imaging Uranus from the ground. Now, Voyager will get so close to Uranus that we will be able to resolve features that are just 2 or 3 kilometers in size. Uranus's diameter is more than 50,000 kilometers, so you can see that there's just no comparison. We will improve the resolution that you can get from the ground by a factor of approximately 1,000 or more.
Pictures from space are, of course, the highlights of each day during the encounter. The imaging scientists, the people in the image processing lab, and finally, the technicians in the photo lab work throughout the day and night to get the best pictures from Voyager ready for the news media each morning. Those pictures are released, along with the other scientific results, at a press briefing each day. Bill Griffith was on hand this morning as Voyager scientists reported on their latest findings.
Voyager scientists had some more answers about Uranus's magnetic field at this morning's press briefing.
We have detected firm evidence for the existence of a Uranian magnetic field, substantial in magnitude and influential over an appreciable region outside of the planet and its atmosphere.
Earlier, it had been estimated that Uranus's magnetic field was about 1/10 the intensity of Earth's, but it turns out it's about half the Earth's intensity and very flexible.
The magnetopause of a planet's magnetosphere is not a rigid boundary, but it's pliable. It's somewhat like having a balloon in which the amount of pressure or total gas inside is variable. And so this magnetosphere can expand and contract, and correspondingly the position of the bow shock will vary as the size of this obstacle to solar wind flow increases or decreases. What are the implications for the interior? Well, it means that there is a conducting fluid inside the planet which is being stirred by some convective motion, regeneratively amplifying a magnetic field which we observe externally. We don't know the characteristics of that magnetic field in sufficient detail to infer yet what the characteristics are of the interior, but after we have the full suite of data obtained from our flyby, we hope to be able to do just that.
Imaging team leader Brad Smith showed this color image of the planet's rings, indicating that the rings labeled epsilon, beta, and alpha are the same color, while rings gamma and eta are different colors. Scientists say that this suggests that while some rings may appear to be the same size, the particles that make up those rings are of different sizes, hence the different colors. Smith also showed this rather intriguing photo of Miranda with an unidentifiable chevron-shaped image on the surface. The good news is that when Voyager focuses on that region during its closest approach, it will produce the highest resolution images of any surface Voyager has yet photographed during its mission. And the best is apparently yet to come as Voyager begins sending back all the information that it gathered during this morning's closest encounter. With today's press briefing, I'm Bill Griffith.
Anyone who's ever taken a snapshot knows you need enough light for the camera to work properly. But what are you to do when you're 20 times farther from the sun than we are here on Earth? When the sunlight on a bright day is only 1/400th as bright as it is here for us. The Voyager team figured out a way to solve the problem, and Dick Laser, the project manager, is here with me to explain it. Dick, how can you tackle a problem like that? You can't change the film.
Yeah, well, let me generalize the problem a little bit. We have to worry about blurred images, about smear. And there's three causes of smear that we worry about. One is long exposure times, and I'll get to that in a second. Two is moving the camera. These are the problems that your everyday photographer would have, too. Camera motion and then target motion, like taking a picture of a race car. Let's talk about the long exposure time first.
Okay, fine.
Uranus is twice as far away from the sun as Saturn. That means, inverse square law of physics, 1/4 as much light falls on its surface, or the cloud tops. That means 4 times the exposure time. There isn't a darn thing we can do about this. We're out of luck. We don't have headlights on the spacecraft or a big strobe or anything like that. We're stuck with that one. The other two we can work with. Okay. In order to explain spacecraft motion, I have to talk about the spacecraft a little bit. The spacecraft is a 3-axis stabilized spacecraft, 3 orthogonal axes, and the spacecraft tips back and forth in each of these axes, and each time it reaches the edge of a deadband, one of these little thrusters is commanded to fire, and then it drifts off in the next direction until it reaches the edge of the deadband and then fires again, and so on. The time period between each pair...
Those are the control limits.
Those are the control limits.
The sensor knows when it's gotten that far, it says do something.
These limits are set at plus and minus 0.05 of a degree.
It's rather small. Mm-hmm.
That's right. And then one cycle is about 4 minutes across, typically. And as I say here, the typical spacecraft in yaw, one of the pitch, yaw, and roll, the 3 axes, is about 0.05 of a degree per minute. And if we compare that with the rate of motion of the hour hand, the little hand on your clock, it's about, you can see, 1/10 the amount.
10 times slower.
10 times slower than the hour hand of the clock.
Like that.
Okay, now let's...
but you're not satisfied with that?
We're not satisfied with that by no means. We worked hard over the last few years to overcome this problem. And what we did was get right down into the heart of the attitude control system of the spacecraft, and we modified the software on the spacecraft so that we reduced the electronic pulse that controls the actuation of the thruster. And as you see in the chart here, this is the same as before. That's the normal pulse firing. What we did was reduce the number of molecules of gas that come out of that thruster each time we fire, so that in fact we've doubled the time between firing.
Drift rate is so much slower.
That's right.
I understand to do this, you actually took the identical kinds of thrusters that are on the Voyager out of bonded storage someplace here and requalified them for space use.
At this particular mode, this is a completely different use of the actuator than we ever planned to do back in 1970.
You're not just redesigning the computer, you're sort of re-engineering the spacecraft.
That's right. Absolutely.
Okay, so that means slower motion.
Slower motion.
So one of the causes then
is eliminated or reduced by 50%.
Okay.
By that fact. Okay. Another unique problem that we have with this spacecraft is that each time that this little tape recorder, it's a little bit bigger than your home cassette recorder, and it has a motor in it. And each time that we start or stop the tape recorder on the spacecraft, believe it or not, it torques the whole spacecraft around. Okay? A problem. And we see on the chart here what happens. Here we are in our normal limit cycle. About this point in time right here, we say we start the tape recorder. And what happens is, if we're going in this direction, it drives the the whole spacecraft over hard. And you see a very steep...
it bounces back for a while.
Very steep. And then it bounces back hard, and we have a lot of firings and a lot of steep motion here. Steep motion means fast motion of the camera, the spacecraft, and therefore the camera, and that means a lot of smear. How do we overcome that?
You got to use a tape recorder for most of your pictures.
That's right, especially at this encounter. You've noticed
Yeah.
We've used the tape recorder a lot. And what we've done is that each time that we get to this point where we have a start or a stop command, we simultaneously on board the spacecraft, in addition to commanding the recorder to start and stop, we send a command to the attitude control system to fire the right amount of thrusters in the right axes to just
So
compensate.
you finesse this torque a little bit. Just
Absolutely.
At the same
We
time.
cancel it, and that's what we call momentum cancellation.
Very good. Okay. And
So
what
those
we
are the
left
things
with?
having to do with the camera motion. Now we have to talk about the target motion. And
we're going by at 33,000 miles an hour.
And we're going mighty close to Miranda. Obviously, we have the same problem as the photographer taking a picture of a race car, okay? And the solution is identical. What we do, here's our Miranda, if you will, moving by. We do this with several other satellites also. And what we do is, with the recorder playing, we slowly move the spacecraft, the whole spacecraft, not the scan platform. The scan platform would be too jerky if we did it, but we move the whole spacecraft very slowly. We literally track in the field of view of the camera the target. And then, what is happening, you can see when we move the whole spacecraft, we're depointing from the Earth.
The antenna is no longer looking home.
That's right. And so that's why we have to, it's one of the several reasons why we have to record. And you've heard a lot about image motion compensation, target motion compensation, same thing.
This is it. I understand you do that. You do that with gyros. By you go on gyroscopic control and you feed the gyroscopes a slight signal says you're wrong, and they continuously try to correct for it very slowly.
Very slowly. Basically, what we're doing is faking out the attitude control system.
And tomorrow we'll see how well you do.
I think we're going to do great. We've had several tests, and the lack of smear in the images that we see tomorrow will be demonstration.
Very good. But you have tested this system, then?
Absolutely. We've used it some in tests using star backgrounds on the way to the planet.
Thank you very much.
Sure.
Yesterday, Lonnie Lane told us about an experiment called star occultation. That's where a star passes behind Uranus rings, and Voyager's photopolarimeter measures light from that star. The experiment took place late last night, and Bill Griffith was there.
The plan was to use the star Sigma Sagittarii to backlight Uranus's rings with Voyager's photopolarimeter. Scientists would take as many as 100 images per second, giving them a very clear image of the ring's true structure. The first critical moment in the process came late last night as Lonnie Lane and his team waited for confirmation from Voyager that it was all set to perform the occultation.
Tonight we're right now trying to see, will the instrument set up in the proper field of view? The instrument has several different size of apertures. It's on a wheel. We've been having some trouble with that wheel because some polymer buildup on the electrical contacts, so it slips and sticks. And in the past we've had some difficulties. So we just executed about 2 hours ago a sequence that rotated the wheels back and forth, end to end, very slowly, and allowed them to try to clean themselves. And then we have 3 measurements that try to address itself to the 1 degree and then back to a safe. And we hope that'll do the last cleaning, and then when we set up, we'll be in the right place.
One potential problem added to the drama, the tracking site in Madrid, Spain, which would be receiving that critical occultation data from Voyager, was under a cloud and rain was forecast.
The weather situation is such that the data we're bringing down has very little protection code on it. We're operating in the type of data mode that does not have extra Reed-Solomon coding and other things to protect the data. So at the data rate we operate, we're very sensitive to water vapor and rain especially. If it rains, we're in trouble because the data will not make the antenna with enough energy coming through to let us get the signal and lock up. Now, the predictions were relatively nice weather in the latter part of the day at the Madrid station, seeing potentially some rain. So we've been very carefully balancing when does the data come down that's critical relative to when the rain might start. The problem is Spain does not have large-scale weather patterns that are very small localized. The weather can change in 45-minute centers. This thing lasts almost 4 hours. And it's a gamble. If we try to protect the data by a real-time command, we would lose one of the supporting experiments. And so I guess we decided to sort of go for broke, hope the weather's okay, and try to get both experiments to measure at the same time.
So Lane and his team spent a few anxious moments waiting to see if their 4 years of planning would be successful or all for naught.
Everything together, yeah. If there had been a change.
Plus 15.
You wanted anticipation, you get it.
This is a watch hot.
Then, around 10:45, they got their answer.
Data's on the ground now. There.
All right, to all my friends who made this one possible, thank you. Let's see if we get some good data on this.
This morning, Lane and his team were still on the job, poring over the clear images of the rings that Voyager had sent back. And the good news was it hadn't rained on their parade after all.
It didn't rain. We had a very small amount of interference. Things worked very well. We have most of the data we want. We crossed the total of 2 rings inbound, 2 rings outbound, the same 2. They are different. We see geometry changes. We see extremely interesting fine structure. I think we're going to give the theoreticians a field day trying to explain some of the fine structure we see. That is, the gross models will probably fit with the data. But in fact, the very high resolution in the rings is going to cause some theoreticians a few sleepless nights trying to understand what happened and why.
At JPL, I'm Bill Griffith.
Those were exciting moments for Lonnie Lane and his team. Now, Lonnie's here with us to tell us more about it. Lonnie, how did it all work out? I understand there were a few sort of nervous moments.
Yes, every occultation we've worked on so far has had them. The sticky wheel was one question, the aperture. This time it's set up just properly for the Sagittarius occultation. We got right where we wanted to be, and you saw on the film that everybody was very pleased. We realized a large team has worked very hard to make that happen, including a real-time command sequence that got fit into the spacecraft barely 2 days before closest approach. So a lot of hard work on that.
And then there was also a little bit of a scare about weather over the tracking station that was perhaps going to cut down the data.
That's right. This particular data set had very minimal protection on it, minimum code protection, and we're very susceptible to weather. If it had been raining, we would have lost the data, and there's no tape recorder on this set because we need it for near encounter images. So it was a nervous few minutes, but apparently everything worked out fine.
And you did get the data back. Now, the data is now back. You've had a chance to look at it for a while. What do you see?
Spectacular things. The resolution of this occultation, the Cygnus Sagittarius, across just 2 of the rings of the outer part of the 9-ring system, the large epsilon ring and a very narrow, small delta ring. The interesting thing about it is that there are certain limitations from the ground in the optical domain, mainly because the size of red stars used by ground occultations, or potentially from space telescope or very large aperture things in Earth orbit. So they're sort of limited by the physics of the way light diffracts around particles in a ring system, which says on the ground or in Earth orbit, for everything except maybe a super long-range baseline radio system, you're limited to about a kilometer resolution. And some of these rings...
Anything smaller than that is just a fuzz.
There's going to be a fuzz and ill-defined at best. With this particular occultation, because we're so close, and high sampling and using a relatively small UV light source, a star, we were down to 10-meter resolution approximately. And as I say, that's much better than anybody's going to have for a long, long time. The structure inside the epsilon ring is extremely complex, and we're trying to sort it out based on models similar to things we've learned at Saturn. Question of whether some resonances or the shepherding satellites or embedded satellites cause these kind of very rapid oscillations in the density of material in the rings.
Is it, now that you see it in the finer structure, is it one ring or are there breaks in it?
At the moment, we have seen no breaks, so it's sort of at least at the underlying level of potentially fine dust, it's continuous. What we cannot separate out from our experiment is our larger particles, baseball-sized or meter-sized objects, or maybe even larger, segregated into channels within the large ring structure, or maybe a 15-mile-sized ring. To that end, we're dependent upon the radio experiment, the radio occultation is occurring right now, to sample out the larger particle domain. And then we assimilate the visual images, the radio science data, the photopolarimeter data, together to get a span of particle sizes and then the nature of the way everything fills together and makes that system work.
You're going to have another occultation of the ring system.
That's right. It's completed. We've seen our first quick look of it, but only half of it because most of it's on the tape recorder.
That portion is tape recorded.
That portion is tape recorded, right. And so we will wait to see it when it comes down.
And from the first quick look, does it look again like a complicated structure?
Yes, indeed. We have all of that and maybe some very nice surprises. We've got our fingers crossed, a little bit more data analysis, and next day or two, those stories should be coming out.
Thank you, Ronnie.
You're welcome.
Of course, there are other experiments that have plenty of suspense for their science teams, too. One of those began early this afternoon and ended just 14 minutes before we went on the air. David Sparks visited the radio science team as this report.
Television shapes all of our lives as an information source. This is underscored by the fact that we are watching the encounter between Voyager 2 and Uranus on television every night. Well, the people in the radio science department of this entire venture might suggest that they have an awful lot to contribute to this mission as well.
What we do is we use the combination of the spacecraft, the ground station, and the radio signals traveling between the two as a probe to measure, to reach out and touch, if you will, these remote planetary bodies. While Voyager 2 is passing behind the Uranian system, it first passes behind the rings and then behind the atmosphere. The radio waves from the spacecraft to the Earth will be passing through the rings, received on Earth, then passing through the atmosphere and received on Earth. We measure on the ground at the Earth station in Australia the characteristics of those signals.
From an intuitive point of view, it might seem that the imaging team, because they use cameras, would gather more information about the physical size and shape of Uranus and its associated structures. Dr. Len Tyler and his team of radio science people put an immediate end to this notion.
Our measurements are much more abstract. They're quantitative, and they relate to structures that can't be seen in the images. For example, we're sensitive to the size of the particles in the ring system. Those particles may be in the size range of marbles or ping pong balls up to boulders, and those are far below the resolution of the images. In the case of the atmosphere, as the radio wave cuts through the atmosphere, we penetrate to levels that may be below the visible portion of the atmosphere, or may be in parts of the atmosphere that are transparent.
Dr. Tyler's team has been preparing for months to gather data during the Voyager 2's period of occultation, when it disappears behind Uranus. The months of planning turn into a few hours of very intense excitement.
In the case of the rings, we learn about the size of the ring structures. We learn about the size and the distribution of sizes of the ring particles. We should be able to make extremely precise measurements as to where these rings are located, certainly on the order of 100 meters, which is about the size of a football field.
Let us try to put this all into perspective. Measuring objects the size of a marble and locating rings within 100 yards over a distance of 2 billion miles 8.5 years after the spacecraft was launched, one wonders if you really can put this all into perspective. I'm David Sparks.
The occultation by Uranus ended within the hour, but we're still waiting for the second ring occultation, and now Von Eshelman of the radio science team has dashed over here to tell us about it. And welcome, Von. What can you tell us this early in the whole process?
Well, we're very excited. The very complex maneuvers of the spacecraft to keep it pointing in the proper direction as it went behind the planet. And also, during the time that it went behind the rings, we know we have data and that the spacecraft came back to the correct position after it cleared the planet. And for several hours now, we've been taking data. I actually left before I saw the signatures of the rings coming out, but I saw them going in. We see every one of them. We maintained a signal all of the way through the occultation. Now, when you think about the fact that we're about 2 billion miles away, transmitting from a spacecraft with about 20 watts of power, where the atmosphere refracts the signal in a way that diminishes that power by a factor of several hundred, It's as though you're dealing with a tenth of a watt over a couple billion miles and picking it up and not losing it during the time that the spacecraft was behind the planet.
So the signal's here. Now you have some time. You can relax and analyze it and tell us what's the complete structure of the atmosphere of Uranus.
Well, the support team and the science team and the people in Australia are just so happy that everything has turned out so well.
You have a diagram here showing how that power cuts off when we go behind it. What happens?
Well, just let me illustrate the rings first. We have a view of the plane of the sky with the spacecraft moving from the right side to the left side with time. Spacecraft right now is about in this position in the plane of the sky. It has just cleared the rings coming out of the occultation behind them. The circles are indicative of the size of the antenna beam, but that's not too important relative to the ability to make measurements. We did see the rings illustrated here just with some marks going in, and the signal strength was reduced as much as 15 decibels over, which is a factor of about 30, another about 3% of the power that it would be without the ring there. That immediately tells us, for example, that these are not dust rings. There are substantial sized particles there. The atmosphere itself, and let me say a few more words about it in the next illustration. It's a little bit better to talk about the atmosphere. Here, blowing up that central part, again, the spacecraft trajectory is from right to left. Now, it then passed behind Uranus, as seen in the plane of the sky. And the distance, when it's right at this position, for example, the direction to the limb from where we see it is about 3 degrees off the direct.
Now, do you re-aim the spacecraft?
Yes, the spacecraft now must go into a complicated dance in space in order to maintain the direction to a very high precision to aim at this point along the limb
You
of the
actually
planet.
track right along the edge of the planet.
Now, it looks very similar to what some of the logos on some of the television programs have about a glint that goes around a circle, if you've ever seen those things. That's what you would see with your eyeball. If you could see the radio waves, there would be a strong glint moving along the periphery. It moves faster when it gets to this point. In fact, even though the spacecraft is going in the plane of the sky only about 8.5 kilometers a second, that glint is moving at 20 kilometers per second.
And so from the data gathered up along this curve, we can now tell something about what is doing the absorbing in the upper atmosphere.
Yes, it's primarily the question of the structure of the atmosphere. It's temperature and pressure.
So thank you very much, Ron.
Well,
Uranus, just like Jupiter and Saturn, has rings, but Uranus rings are as dark as charcoal we use in our barbecues. In fact, they were only discovered by noticing how faint starlight from behind them was cut off as it went through them, much as it was in this experiment we just conducted. They weren't discovered until 1977, and the first photographs of them weren't taken until 1984.
The rings of Uranus. Then I think it would be fair to ask you how the rings of Uranus compare to the rings of Saturn and Jupiter.
Okay, well, our ground-based photograph actually came only in the last year or so, and the rings were discovered in 1977 from the ground.
But you photographed them.
Stellar occultations, right. What we've learned from that data are that the rings are significantly different than the Jovian ring system and the Saturnian ring system. Different in the way that the known rings from the ground are very, very thin, very, almost like little necklaces around the planet with very, very much open space between them. Now, at Saturn, we of course, found a ring system which was full of material and a very colorful structure, very colorful, very variegated in style and texture. At Jupiter, we found a very, very thin ring associated with 2 or so moonlets within them. Now, one of the big mysteries that we've had for a long time from the ground was why do we not see an association in the Uranian ring system with satellites, with moonlets, as we do at Jupiter and as we do at Saturn? So one of the exciting things about this project is that we want to go there to look for those moons associated with the rings. We know that the moons of Saturn, for instance, give you all of that undulating detail within that ring system. So now that we're finding new satellites around Uranus, we're hopefully now going to associate that with the ring structure. And associated with these new moonlets, of course, we may be unfolding, even now, new ring structures as well.
The research that has taken place up in the spacecraft is on a recording device, right? When you start getting all of that back and looking at it, can you give us a guess as what you're going to see? Is it possible? Is it fair?
Well, it's a madhouse right now in terms of analyzing the data. We're getting back new information. Each picture we get literally is something new that we've never seen before. And I think that's going to typically in these encounters, the one thing that happens is that we get a lot of unexpected results, and it takes sometimes many months to unravel it all. But certain things you can get right away. New ring structures, new moonlet structures, and these interactions are coming moment by moment now.
You wouldn't want to guess how many more satellites you're going to find? How many? And there may be a lot more rings, you say? You think?
Yes.
You hope?
We hope.
Because that's your area of expertise,
Well,
isn't it?
From the ground, we know that there are these thin, almost easy to see rings because there's a lot of material in a very, very small amount of space. But these broader rings, which have very little material, they're thin and translucent, are the ones that are harder to see, and the ones we can see as we get back behind the planet and see them from a different sun angle.
It's an exciting time for you, isn't it?
It's very, very exciting.
I can tell you love your work.
Yes.
And I'm enjoying what I'm doing. It's been a pleasure talking to you.
Thank you.
I'm George Fenneman.
Rings of Uranus are indeed a puzzle, and to help us solve it, we have Rich Terrell with us here. Now, Rich, what did we learn in the last few hours?
The last few hours, we got our first images right around ring plane crossing. Of course, the best images will come down tomorrow. The images in ring that were taken at the moment of ring plane crossing.
Looking right along the plane,
right.
The ring plane, you're one behind the other.
Right. And what's nice about that geometry is that the rings are very compressed, and with one image, we can look down the entire long length of the ring system, looking for shepherding satellites and for faint ring material.
And the shepherding satellites, we found a couple of them, didn't we?
Yes, so far we found 2, and we expect perhaps we'll find others. We have our best sequence for finding the shepherds has already occurred, and we're in the process of searching through that. We found 2 fairly large ones.
You have one of the pictures that shows them both at the same time, which seems like an almost magical coincidence.
Right, we were lucky in that, but we have 2 satellites, one on either side of the bright epsilon ring, one inside, orbiting between the rings, and in fact this satellite solves one of the mysteries, and that is, are we going to have 2 shepherds for each ring, or can we share a shepherd? Quite clearly, the epsilon ring and the next ring, the delta ring, can share this shepherding satellite.
It's about equally spaced, roughly equally spaced between them, isn't it?
Right. We have a close-up view of this inner shepherding satellite, and it turns out that we can now resolve the satellite. And it's somewhat larger than we expected, and it's about 30 kilometers in diameter, and it's as dark as a piece of charcoal.
The same, then you'd guess it might be the same material as we're seeing in the rings.
Could very well be part of, or the same material that the rings are.
30 kilometers is a pretty good-sized object. That's bigger than a lot of asteroids.
Right, right. It's amazing we can photograph something as dark as charcoal against the black background and the light.
This particular picture here is absolutely gorgeous, but somewhat confusing. What am I looking at?
Okay, we're looking at a color process here. It's a color average of the ring. So what we did was we had to add up all the light from an entire image across many thousands of kilometers of ring and essentially make one line of data, a radial profile in color. We've extended that radial profile across the entire image to make kind of a pseudo picture of the rings. But what it does show is that the bright epsilon ring here is colored white or neutral. It seems to have a gray color. But the interesting thing about it is the other rings do show color differences. And this is quite unexpected.
Really? We saw color differences in the rings of Saturn, for example.
Well, the rings of Saturn are quite a bit more massive, and perhaps there are different processes acting on them. We know that the rings of Uranus are all quite dark, and at least what we knew from ground base, they were we thought they would be fairly uniform.
Ah, I see.
But we're finding that rings, these 2 rings, the delta ring and the gamma ring, which appear to be quite similar in most of our previous imaging, appear to be different colored objects. Does
this imply that they come from different sources?
Well, we don't know. That's one of the mysteries we're going to have to think about for quite a while, and perhaps some of the other data, high-resolution data, will help us resolve that.
Because perhaps a completely different material then might have broken up to form each of these rings. Or something of that sort.
That's right. The mass of one of these rings is comparable to one of these shepherds in terms of size.
Thank you very much. We're getting pictures from Voyager that could be called historic in their importance, and I thought I'd take just a minute to show some of them to you. So relax and watch as we take a short trip through some of the pictures over the last few. This is just Uranus from a long way off, taken some time back. This is a small moon Miranda. It is very exaggerated in this view because this particular one was taken to help the navigation team. This is the moon we're going to come very close to, and in order to find out exactly where it was against a star background. Now, not all those white spots are stars. Some of them are just noise. we took this picture of it. Aerial, this is one of the closer ones we got before those that were taken this afternoon that were recorded for later playback. And another picture of Uranus. Several of these were made at the time we were also looking at them with the spectrometers. The rings, another view with some light of Uranus shining on the innermost portion, and the moon Umbriel, one of the others we'll get a closer picture of. Uranus again, and here rather sharp filtering to bring out some of the atmospheric characteristics, and Oberon, finally Titania, the one we showed you at the opening of the show. And now back with us once again is Dr. Ed Stone, the project scientist. Ed, let's try to recap the day if we can, and what would you say has been the biggest accomplishment today?
Well, I think the major accomplishment has been actually having the spacecraft execute, as far as we can tell, exactly the plan that we had laid out, and including, as we've heard, the very, very precise radio occultation, very complex set of activities on the spacecraft. Everything has, so far, has been going very well, and that has been certainly the major accomplishment today.
It has indeed. It's been a phenomenal mission. After all the changes we made, sending the commands right up to the last minute, even after it was executing the last series of commands, we modified it. It accepted all this.
That's right.
And the discoveries we've made today, of course, the magnetic field stands out. Do you have any expectations about the pictures we'll see tomorrow? It's sort of...
Well, of course,
business.
the main imaging that's returned tomorrow will be the best images of the satellites. They'll be coming back tomorrow afternoon. And as we've discussed before, there are some features which show up in these images that we have to date, which are rather low resolution, which look like they may be impact craters with rays. And there are other features on the satellites which are not recognizable. And that may mean we're in for some surprises once we, in fact, can image these things carefully enough to see whether these are just colors on the surface or if, in fact, there's topography, there's relief associated with these features.
One thing we have touched on very little is your own specialty, cosmic rays and charged particles. Could you say just a little bit about how that's going, how those investigations are going?
Well, we're currently right in the magnetosphere. We're measuring the trapped particles, the particles which are spiraling around the magnetic field, bouncing back and forth.
Like our own Van Allen radiation belt.
Exactly, like our own Van Allen radiation belt. And what we're trying to do is determine exactly what the shape and configuration is of the magnetic field and of the population of particles trapped in that magnetic field. And again, we're now more than halfway through, but we haven't gotten the data for most of the magnetosphere yet. That will be coming back tomorrow as well.
That's also being recorded?
Yes. Mm-hmm.
And what about the higher energy cosmic rays? They're also affected by the magnetic field, aren't they?
They're excluded by the magnetic field. In fact, during this time, our sensors will be mainly responding to the particles which are trapped inside the magnetic field.
The lower energy.
Mm-hmm.
And also there's various waves, plasma waves, and other phenomena going on. How are those experiments also giving us information?
Yes, again, especially the plasma wave device, the planetary radio astronomy will be, we may well find something quite different on the dark side of Uranus than on the sun side. There's no reason to expect the two should be different because the sun side is in the sun for so many years at a time, while the dark side is very, very dark for a long time. It may turn out we'll have a rather different ionospheric mechanism there, and we may well have a much different magnetospheric mechanism associated with this long tail.
Spreads out quite a ways behind.
Yes.
Thank you very much, Ed. So we come to the end of the day. We have seen some new evidence about the nature of the atmosphere of Uranus, and we've heard the first direct evidence of a magnetic field which surrounds that planet, and one which we hope very much to find. Well, we won't be here tomorrow. We'll be back the same time Sunday evening, however, as we continue to watch the encounter of NASA's Voyager 2 spacecraft with the planet Uranus. And please, won't you join us then?
Channel 8's ongoing presentation of Space Probe 8 is made possible in part by grants from KTAR News Radio 620 and from KTAR News Radio 620 and the Greyhound Corporation. Of space exploration.
Hello, I'm Al Hibbs at the Jet Propulsion Laboratory, and we're watching NASA's Voyager 2 on its encounter with the planet Uranus. This week, we're looking over the shoulders of Voyager scientists as they receive new information on Uranus and analyze it in its original form. We'll be discussing its significance, the mission's scientific goals, and what this encounter can teach us about our world and the universe. Today, Voyager 2 has traveled beyond Uranus and is looking back over its shoulder at the receding planet, its satellites, and its rings. At 5 p.m., Voyager was 2,544,000 miles beyond Uranus and on a course for Neptune at 33,178 miles an hour. Though Voyager's en route now to Neptune, its encounter with Uranus has not ended. We'll continue to make observations of this intriguing planet for about one more month. Closest approach occurred on Friday. The pictures taken then were not fed back at that time, though they were stored in the spacecraft's tape recorder and have been coming in since then. So let's take a look at some of them. Dr. Ed Stone, who's the Voyager project scientist, is with me now. And the most intense period of our encounter with Uranus is almost at an end, but the encounter continues. Voyager 2 is continuing to look back and take data. And Ed, while this continues, how would you summarize what we've seen, well, particularly today? This has been the most exciting one.
It certainly has been the most exciting day, and I think certainly the highlight has been the images, the close-up images of the satellites in orbit around Uranus.
I think we have some of those available here, and why don't we try to get some of them called up and we just saw one. Here is a reasonable close-up of one of Ariel, but the one we really want, I think, is Miranda.
That's Miranda, yes, that's right. Mm-hmm. I think the thing which surprised most of us was not that Miranda necessarily had all these tectonic structures on the surface, but that there was such a variety, that it was really a very complex distribution. And I think the other thing that surprised me was the extreme relief, which seems to be present on the surface. It's not a very subtle property at all. One sees very sharp scarps, ridges. One sees grooved terrain. One sees terrain similar to that which we saw on Enceladus, which is somewhat twisted. It's just a remarkably complex surface.
And are those cliffs up at the top?
Those are very high cliffs, which are quite remarkable. They terminate a very rugged, hilly terrain, which may well be a place where there is a basically lateral thrusting.
And down at the lower portion of the planet, well, this planet, we call it a planet, it looks like one,
yes,
doesn't it?
that's right.
This moon, Uranus, we see again some of the same curious lines that are going through.
That's right, that's right. Fractures. The surface has been heavily fractured by some sort of processing. There may well be some layering on it in the lower right-hand portion of this image where one sees these alternating dark and lighter streaks. That's right. Perhaps that's layering of material. It's really a remarkably complex surface for an object that's barely 300 miles in diameter.
And this is a picture that we had up earlier, and again with this in this region here.
That's a groove terrain, which is quite reminiscent of the terrain that we found on Ganymede quite extensively. It was a terrain that separated the older, darker parts of the crust on Ganymede.
And this one, with a curious thrusting of material dark here into a lighter group here.
That's right.
It looks like the kind of, almost like tectonic activity you might expect on Earth, certainly.
Yes, well, linear fractures, it's just remarkable that this small object has such a variety of such forms on its surface. And of course, there is an area there which is just ancient, heavily cratered, rather nondescript surface.
And this is a piece of the feature we were seeing before. It curves around in a rather large square, covers quite a bit of the planet.
That's right.
And here's another one.
Yeah, now this is now aerial, and it shows also a remarkable amount of relief. Again, it appears as though there were fault lines which intersected, and there seem to be valleys and perhaps material on the valley floor. Not as dramatic as Miranda. It's a little bit further from Uranus. Whether that has anything to do with the degree of activity on the surface is not yet clear, but it is true that Miranda is by far the most complex surface.
We've looked at a lot of moons over the time that we've been flying Voyager through the solar system. We've seen some rather odd things, like Mimas near Saturn with that huge crater in the middle of it, and volcanoes on Io probably. It's not likely we're going to see anything quite that spectacular.
I think that's right.
But for geologic confusion and fascination, I think this is the one.
I think this must be the prize, yes.
We also saw something else I'd like to bring up here if I can find the right picture for it. Maybe I can't. It's, yeah, let me try to get this one up on our still stories. It just came in today, and with any luck, I will be able to no, I'm not having any luck. But at any rate, it showed the rings, but now backlighted.
Yes, backlighted.
And they were, the dust we've been looking for all along is now there.
That's right. We did manage to take one exposure, 96 seconds long, with the wide-angle camera, and that was enough of an exposure that this very faint dust material just appeared in this image.
And was it the length of the exposure?
I believe it was, because we had shorter exposure, 15 or 16-second exposures, where there was just no evidence of the material.
Yeah, it was quite a disappointment for a while. We expected the dust to be there. Now here it is.
That's right.
But now that we see it, we don't know quite how to understand it.
It'll take a while to understand the complex. That's right.
What about the rest of the things? The magnetic field is still...
well, I think we're learning more about the magnetic field. We've learned that there's indeed a trapped radiation environment. There's enough trapped protons there that if there is methane on the surface of any of these satellites, it will be turned black, in the order of 100 years.
We're seeing
and that may account for some of it, yes.
Thank you very much, Ed. And now I want to point out that the encounter with Uranus is indeed almost over. The encounter continues, though. Voyager 2 is looking back at Uranus to take data, and Bill Griffith is in the spaceflight operations watching the progress of the encounter.
That's right. The people here in the spaceflight operations facility are only one small part of the effort to keep Voyager 2 doing the job it was sent to do. We shouldn't all forget those people who are not on camera every day. Voyager, like any space project, is a team effort. And when this encounter is over late next month, Voyager will be on its way to an encounter with Neptune, of course, the 8th planet from the sun. And these people you're seeing here will still be here, keeping an eye on their spacecraft. Voyager's Neptune encounter will bring the planetary exploration program to the end of its first major phase, that being the initial reconnaissance of the solar system. But there are certainly more projects. There's Galileo, to spend almost 2 years orbiting Jupiter. Ulysses will explore the poles of the sun, and a new spacecraft called Mars Observer will return to the Red Planet. Then there'll be a project named Magellan to go to Venus to map its cloud-hidden surface with radar. While we've learned so much from the Mariners and the Vikings and the Voyagers, we still have a lot to learn. And the people who fly these spacecraft, as well as the scientists who reap so much from the data we get, are our teachers.
The rings of Uranus have provided some thrills and surprises for several of Voyager's scientists, those who specialize in studying planetary rings. One of those is Dr. Jeff Cuzzy from NASA's Ames Research Center, and he's with me now. And just let's talk about these strange rings. And I'm going to ask that somebody can to put up on one of our video ports this picture we want. Vic, could you do that? We're trying to get 7761 to take a look at. Jeff, the rings have been, well, we knew about that they were there before Voyager got there, but we've discovered quite a bit more about them, and particularly about the detailed structure since we've been there. What can you say about them?
Well, you know, the main rings of Uranus, Al, were known from stellar occultations. Several of us who think about rings tend to associate small objects, debris, if you like, were left over from the formation of the moons and the planet that are associated with rings. When you have all this debris around, with the impacting meteoroids that are always there, you always expect to have dust. Now, this dust is very short-lived because it drags into the planet, it gets destroyed by the magnetic field, spread away, one thing or another. So the location of the dust is a very important tracer of where the material is. And so we were very eagerly anticipating the existence of the structure of the dust. Now, because of the magnetic field, and probably because of the perturbing effect of the magnetic field on the charged particles that are small, most of the dust seems to have been removed from the Uranus system. But in the latest images that have come down, which are at the very highest phase angles, that is the smallest deviation of the sunlight from the direction in which it came.
We're looking almost into the sun.
Almost into the sun, and that's how these small particles scatter the strongest.
And this is a picture we got at that point.
Yeah, that is an absolutely spectacular picture, and it shows basically that most of the region of the known rings is more or less replete with dust, and the density of the dust varies, and we have all these fluctuations in the brightness.
These marks here, are those stars shining through?
Yeah, those are stars that are smeared. This observation was taken simultaneously with the radio occultation of the planet, and so we carefully designed these images so that the smear of the spacecraft would be right along the rings. And in fact, the left-hand side of the image is essentially unsmeared for this reason.
The position of this dust, how well correlated is it with the other rings? Are we seeing the main rings through the dust? Or do you know yet?
Somewhere in there we're seeing the main rings, and we're working on that right now. I wouldn't say that the correlation is outstanding. There's just so much stuff there, and as you know, the main rings, there's 9 of them, and this region is completely filled with dust of various density, and so there's a whole bunch of other stuff going on here that we're just going to have to think about.
When we were talking earlier about the magnetic field having a major effect on small dust particles because they get electric charge and then they're subject to electromagnetic forces, this wobbling magnetic field you had anticipated would throw the dust completely out of the system, and yet here it seems to simply have smeared it out in the plane.
Well, it does throw it. It decreases its density, let's say that, because not all of the bigger dust particles will respond less readily to the magnetic field perturbations. So basically, we're just seeing a depletion of the dust. You can rinse your glass as often as you like. You're always going to leave something behind. And this is what we're seeing. The density of this material is considerably less than what we saw at Saturn.
I see.
In the main rings, okay? This is certainly more than we see in the G ring and the E ring and the very, very faint rings. But it's there. It's less than we thought, but it's there.
Jeff, thank you very much.
Okay.
Reporters from around the world are here to cover Voyager's flight. Bill Griffith was on hand for today's press briefing.
Voyager scientists put on quite a show at today's press briefing, and satellite Miranda was clearly the star. Larry Soderblom of the imaging team displayed the very high-resolution photos that Voyager took of it on Friday, showing a surprisingly wide variety of geologic features, groups of canyons and cracks and craters suggesting a violent formation process. Soderblom said that these and other photos are helping them understand more about the formation of the Uranian satellites.
Oberon, we didn't see a lot of evidence of tectonism. Titania, we start to see more evidence. I'll skip over Umbriel. We'll try to work on that one tomorrow, as it's a different story related to its albedo that we've mentioned. Moving on in, Ariel shows a great deal more geologic activity.
There was also new information about the rings, including this photo showing clear evidence of the newest ring discovered. And Dr. Lonnie Lane showed tentative evidence of other formations within the ring complex, including tiny strands of ring material measuring as small as 10 to 50 meters across. There was also possible answers about why the satellites and rings are so dark. It seems the methane ice in them may be interacting with what scientists are finding to be an overabundance of high-energy protons. Yesterday, scientists said they had found that Uranus's magnetic field does not correspond to its rotational axis, that in fact it is tilted at a 55-degree angle from the axis. Today, they said some of the satellites orbiting within that magnetic field may be scraping bits and pieces of it away. Finally, there was even an audio presentation today. Plasma wave investigator Fred Scarf played a recording of dust particles hitting Voyager's electronic microphone as the spacecraft crossed the ring plane from as far away as 68,000 miles. It showed evidence of a vast number of dust particles even at that distance from the planet. With the day's press briefing, I'm Bill Griffith.
We've been talking mostly about Uranus, its satellites, its rings, magnetic environment, what we call the Uranian system. But now Voyager scientists are beginning to compare the Uranian system with other systems. And so Gary Hunt of the Voyager imaging team has joined me now to help us put Uranus into its perspective, the proper one, with Voyager's other targets. And Gary, what the other targets certainly that we have to compare it with are the big gas balls, Jupiter, Saturn.
There's a whole point of this exploration, the other solar system. We can now compare Uranus, tipped on its side, heated so much less than Jupiter and Saturn, and have a look at its weather systems, see how they compare. And when we look at the first pictures that we've actually got, the very first image looks very bland on the left-hand side.
This one here.
And in fact, you can see very little information. It doesn't look terribly exciting. But when you start to bring out the detail using some of the color-filtered images that we have, you can start to see that looking at the South Pole, that is the one we're flying toward, there does seem to be some form of banding around the atmosphere of Uranus itself. You can see, in fact, here going from the polar region out towards the lower latitudes, that there do seem to be bands present. So Uranus at first sight does have a banded appearance. It's worth, in fact, comparing. If we could look back at Jupiter just a second and have to see what that would look like if we look from the poles. This is the view that we have got taking together the previous data from Voyager. Again, you can see how the bands would look if we were flying towards the poles of Jupiter. So we really do have a banded planet relative to the rotational axis. And even Saturn, when we looked at Saturn with Voyager, if you look at the next picture, you'll...
Well, we might point out the little black spot in the middle right here isn't.
That's an example.
Spot.
That's right, because we weren't flying that way. To remind people, we were flying around the equator.
And we never got pictures of
That's the part we never saw. But when we look at Saturn, then the appearance there is once more a banded planet, and the bands, in fact, are here. Here are the bands in this sort of direction, rotational axis down here. So, in fact, the band, in fact, is sort of perpendicular to the axis of rotation. So we're in a position now to sort of summarize the way in which the planets now look. But in fact, it is that the rotation of the planet that, in fact, organizes the flow. And if you look at the summary picture that one can view, then, in fact, you can see that here, with all the planets that we've seen, from Venus to the Earth, through Jupiter, Saturn, and now Uranus, all with very different axes of rotation, but it is the spin and that tilt that organizes the flow.
Not the sun hitting it from one place
Not so much
or
the sun hitting it. So in that aspect, Uranus really is banded. That is a very significant discovery. Exactly why it's banded, we're not really sure in the sense of how the cells mix together, but the rotation has organized it, you can see, perpendicular to the axis of rotation. But here the difference then is Uranus and, of course, the way the weather systems are driven. About a 400th of the energy that reaches the Earth finally gets to Uranus. Very weak sunlight. But in fact, we are seeing cloud elements there. When we look up here to these lower latitudes, this is looking down towards the equator, we are in fact seeing clouds. Now, these sort of cloud systems probably are methane clouds, convective storms. And this particular one we've seen for more than 200 hours, a very long-lived feature. And in fact, it looks very much, in fact, like the plumes that we saw around the equatorial region of Jupiter. So in fact, what we're seeing is that the storm systems that we've seen on the Earth, that we've now seen on Jupiter, on Saturn, we're seeing on Uranus, and although this planet is covered in a haze layer, it has got an active meteorology, strong weather systems, even though it would seem that the sunlight is very weak, and even the internal heat source is of a different magnitude that we've seen from its other companions, Jupiter and Saturn.
And the heat source for Jupiter certainly included its own, the heat that Jupiter itself is putting out.
That's right. Now, this is one of the observations we're expecting to obtain at any day now. We'll be measuring the total sunlight the planet is reflecting compared with that it emits. We understand the energy that the planet therefore has intrinsically compared to that it's radiating away. We'll know just how strong that internal heating is. Now, if there isn't a very strong internal heating and this weak sunlight, perhaps we have a slightly decoupled system from the deep interior compared to the meteorological systems, and we may have weather systems rather akin to the thin models that we tend to use to explain the Earth. But this really has been an exciting encounter, perhaps not terribly many cloud features, but many that's given us a good idea of what the weather on Uranus is doing.
Gary, thank you very much for joining us. Until the dawn of the space age, astronomers were the scientists who studied the planets. But since then, people who pursue many scientific disciplines have spent their time working on planetary exploration. But astronomers are still in the middle of the action, and Karen Long talked with one of those astronomers, Dr. Rita Beebe, about Uranus.
False color global photographs of Uranus are enabling imaging scientists to track weather features and map wind fields on the planet. Astronomer Rita Beebe's been studying this whitish streak across the top of the picture. She says it's the first time in history we're actually able to see clouds at Uranus. How do you know it's a cloud?
Because it's free moving. There is another one which will appear on the limb and follow around here. And the two clouds are separating from each other in time, so that this cannot be rotating like a solid body. There has to be winds in this planet that vary from the equator to the pole of the planet.
Now that little cloud formation at the top of Uranus looks relatively harmless. How big would that be?
This dimension across here is about 1,000 kilometers, or about 600 miles. These are equivalent to cloud systems here on Earth. When you listen to the weather report and they're showing a large mass of clouds that are coming in off of the Pacific and moving across the country, those are large systems. They're 1,000 kilometers across easily. So that what we have is we have an entire convective system that is being sheared in the wind, and we're tracing it.
According to Professor Beebe, the cloud is formed from methane. The visible cloud deck is actually so cold it's methane ice. There are apparently similar clouds all over the planet. In this picture, however, pinkish hazes, or fog banks, are prohibiting deeper views into the atmosphere. Uranus is apparently much like Jupiter and Saturn in that its atmospheric conditions are dictated by the rotation of the planet. Yet we find the weather conditions at Uranus are quite unique. Scientists have not detected any excess heat coming from Uranus, the kind of heat that contributes to violent atmospheric conditions like the stormy Great Red Spot at Jupiter. I'm Karen Long.
Voyager's many scientists specialize in specific aspects of exploration. The planet itself, its rings, its satellites. And one of those who specializes in the satellites of Uranus is Bob Brown. David Sparks caught up with Bob while he was studying some of the latest Voyager pictures.
One of the things that I found most striking about Oberon are these two craters which have very dark floors. That is, the interior area of the craters are quite dark. The exterior area is quite bright. We've had very little time to think about this, but one particular scenario that we have been able to come up with is that this perhaps represents flooding of the crater floor subsequent to the crater formation of some kind of dark material, probably water ice mixed with something that makes it dark. I guess might be carbon, but of course that's a little speculation at this point. So this suggests to us that, at least in some sense, Oberon hasn't been a dead body for its entire existence, that it perhaps might have had some geological activity in the distant past. The other thing that you can see here, which I thought was quite interesting is that there's a small little pip on the limb of Oberon here. Now, it looks small in this image, but it is in fact a mountain which is about 6 kilometers high, or about 3.6 miles.
Fascinating stuff, but how about for a person that isn't quite as familiar with all of this stuff, answering this question, why do these satellites all appear as though they are almost perfectly symmetrically round?
Well, that's primarily as a result of two things: their size and the fact that gravity acts in a symmetrical way. That is, after you have enough mass, excuse me, enough mass in a small enough space, the thing will tend to crush because of its own weight. And because gravity acts symmetrically, it tends to form the thing into a sphere. So these objects are large enough and made of a material that's deformable enough so you can expect them to be spherical. The lower limit of size for an object like this before you expect it to start to get irregular is about 500 kilometers in diameter, or about 300 miles. Below that, there's not enough mass to deform the material so that it can form into a spherical shape. And so we expect perhaps that some of the smaller satellites of Uranus, for instance 1985 U1, is irregularly shaped because it's only about 150 to 100 kilometers in size, as near as we can estimate.
For a little more on those satellites, Larry Soderblom, the Deputy Imaging Team Leader, has joined me. Larry, we have an enormous number of questions that have come up, particularly with regard to the close-ups of Miranda. How are we doing about finding some answers?
Well, we're working on them. The Miranda images really surprised us. An object this small, this remote, out in the cold reaches of the solar system, presumably made largely of ices, some rocky materials, that shows this bizarre collection of geologic activity was beyond our wildest expectations. What we see is a composite of a variety of geologic styles, unlike what we've seen on any planet so far in the solar system, actually including the Earth.
Yeah, this thing up here, which looks like a bed or a bunch of blankets piled one on top of the other.
Right, it does. Right. That's the impression I get as well, is that it looks like imagine a set of playing cards in which each card is a little smaller than one below it. So you build up a tabloid of these, and you imagine, or another way to describe it is sort of rectangular crepes stacked up, and they're kind of floppy. And when you get the stack made up, you slap it on the side of Miranda, and that's...
But we're getting different colored crepes here. There's some white.
There's some white.
White layer,
dark.
Black layer, white layer.
Well, we know that the satellites of Saturn and Uranus, as well as a number of the asteroids, show a variety of bright, dark materials, and their origin's uncertain. Carbon is thought to be a predominant agent virtually in all of the scenarios to explain the dark materials. The bright materials, we've suggested a variety of ices. In the case of Mars, it was carbon dioxide ices, Io, sulfur dioxide. Here, replacing water ice. Methane's been suggested, but it's also been shown that it should be pretty dark. It may be the darkest ice of all. Could be methane here.
But if this is so, there's not only some interesting geologic activity pushing the surface around, but there seems to be some sort of differentiation among the ices.
That's right. Particularly in this layered patch, we don't know how it originated. There are a number of models that the imaging team is beginning to work on.
And here's this one here, which has some very enormous cliffs.
Oh, yeah.
Down here. How can
those are incredible. Well, you see here that, let's see if I can get this triggered here. Along here, you'll see a series of linear fault systems all the way through this region here. One of them, at this point, tears open, generating a series of cliffs. For those of you that are familiar with rim rock country out in the west, you can imagine walking along that rim rock right there. Down is into the screen. That may well be several miles. Vertical drop.
Steep cliff.
Enormously steep cliff to get up and down. Basically, this whole object has been torqued and sheared. Another thing interesting in this particular picture here is the boundary between this train, which is very lineated, and this sort of rolling train over here.
And then down in this region, this sort of jabbing its way up into like it was almost a tectonic.
Right. There's an intersection here between two linear tectonic systems. One of them is highlighted by this bright material down in this region. Probably one of these volatiles, methane, ammonia, water ice, leaking out into the near-surface materials and forming frost deposits. Over here we see a variety of very rolling, irregular, sinuous cliffs. The best model for that is what we saw on the planet Mercury, and that is that the crust has been compressed. Most of these features that we see are due to tension.
And we're seeing only one picture of the whole group here.
Oh, one of the group, yeah.
Larry, thank you very much for joining us.
All right, thank you.
We've been showing you around a lot of the territory here at JPL, the Jet Propulsion Laboratory, where we explore the planets for a living. But someone asked just the other day, what's JPL and how did it get involved in space exploration? Well, Bill Griffiths talked with a couple of people at JPL who know quite a bit about the lab's history.
The Jet Propulsion Laboratory is nestled in the hills around Pasadena, California, just a few miles from the city's other famous landmark, the Rose Bowl. JPL's roots go back to this wash. This is the Arroyo Seco wash, located just east of JPL. It was back in 1936 when a group of graduate students at Caltech, under the direction of Professor Theodore von Karman, successfully launched the first liquid fuel rocket motor. That was the beginning of JPL, and in effect, the beginning of the American space program. But JPL Chief Technologist Terry Cole says that original experiment almost didn't happen.
They were afraid that they weren't going to make it, actually, because of a lack of about $120 for spare parts, which they did scrounge up in Los Angeles. There is an apocryphal rumor that the money was won in a poker game, but no one knows whether that's really true or not. As it turned out, they did fire their first test on the 31st of October, 1936.
The government began formal sponsorship of those students' rocket research in 1939, and then the Jet Propulsion Laboratory itself was formally started in November of 1944. JPL went on to work for the military during World War II on projects ranging from rocket-assisted airplane takeoffs to long-range guided missiles. And then along came the space age, when JPL got involved in the Explorer 1 project, and the lab's long-standing relationship with NASA was born. JPL Director Dr. Lou Allen.
Even during those very early days, JPL was asked to take the lead in certain interplanetary investigations. The earliest Pioneer spacecraft, which escaped the Earth's gravitational field and proceeded on past the moon, were done by JPL. The original programs were the Mariner programs, which investigated Venus and Mercury and Mars, and then that later led to a very comprehensive investigation of Mars, which was the Viking program, in which JPL was responsible for that spacecraft.
And JPL's work in space is far from over. Following this Voyager mission and the so-called Year of Space Science, with Ulysses to the Sun and Galileo to Jupiter, there is a planned mission to Venus in 1988 and one to Mars in 1990. I'm Bill Griffith.
One of the moments in this encounter that held special fascination for many of Voyager's scientists was the instant when Voyager 2 crossed the plane in which Uranus rings lie. Karen Long was there with Rich Terrell, and the pictures from that moment arrived at JPL.
This is the first of 4 images taken by Voyager 2 right at Ring Plane Crossing. Although it looks upside down, this was actually Voyager 2's orientation while making the 5-second exposure. We're no longer seeing full circles, but looking closely at the curve of the rings, the so-called ANSA. We spoke with imaging scientist Dr. Richard Terrell.
What we have in this image is the epsilon ring, the broadest and brightest of the rings, and one of the first of the known rings, the previously known rings, the delta ring over here. We announced yesterday that we discovered a new ring between the delta and the epsilon rings. And actually, if you really tilt your head a little bit and look very hard, you can just see hints of it between the two. In fact, we can use a technique called false color to try to bring that out. And Not sure this will help, but it certainly enhances the epsilon ring. Right here, you can just start to see this new ring.
How wide across would that new ring be? And why wasn't it detected from the ground during a star occultation?
Well, there is evidence in at least one occultation that something was detected there. It's a very, very tenuous ring. That is, it doesn't block out very much of the starlight. It's thin and transparent. Our indications are that it's, I don't know what the exact measurement is, but it does have a finite width to it. It's probably several tens of kilometers wide. And one of the things we're really interested in looking at is if the ring is continuous. Does it go all the way around, or are there breaks in it? Since it does exist in an area near a shepherding satellite, it's probably a very disturbed ring. It probably has quite a lot of perturbations in it and may even be a partial arc.
And that would be quite unusual, wouldn't it?
Yes, it would be. And however, we did find rings like that in the Saturn ring system, and we also think the Neptune rings are like that. So this might be a preview of what we might find at Neptune.
And how could a ring be discontinuous?
Well, it's a complicated dynamical issue, but basically it involves the action of shepherding satellites nearby, disturbing the ring material and concentrating it in certain parts of the orbit.
What new insights are we getting from this particular picture on the rings?
Well, we've got our first information on the real structure at high resolution, the distribution across the orbit of the rings, discovery of tenuous material within the rings. We've got color information on the rings, which indicates they may be, in fact, different material or have different color properties. And
what colors?
What colors? Well,
we've always heard they're charcoal black and nothing else.
Charcoal black, but they do have certain tinges to them. And we don't know whether the tinge is one ring being red and the other being blue or what, but at least one ring is very, very different in color.
Was there any concern that as Voyager 2 was making its ring plane crossing that it might encounter some wild ring particles that are out beyond the known rings?
Absolutely. In fact, it's a very valid concern. We cross well outside these known rings. However, there is ground-based data to indicate there are rings between, for instance, the moon Miranda and Ariel. Fortunately, there was no ground-based data to detect any material in the area that Voyager was crossing the ring plane, so we felt pretty confident, but it's always a concern. We always keep our fingers crossed at the moment for ring plane crossing.
Imaging scientists will be carefully studying the new pictures in the coming weeks and months, looking for tiny shepherd satellites not immediately visible and other peculiarities within the rings. I'm Karen Long.
And shortly after Voyager crossed the ring plane, it flew behind Uranus. And at that point, the team called Radio Science went into action. So that was their big moment, when the radio signal from Voyager began to penetrate the atmosphere of Uranus.
We've been hanging around the radio science team for just about a week now as they have waited for their big event to arrive, the occultation. And that's when Voyager 2 disappears from Earth's view behind the planet Uranus. Well, finally, the moment of truth has arrived.
That's it.
That's something, all right.
Well, we're actually right at this very minute, right in the middle of the ring system. We've seen a radio occultation of 6 rings, and I guess we're waiting for the 3 more rings to see. We're on the ingress period. We're going in. We still got the atmospheric occultation to go, and we've got the rings to see coming out. So we've seen the signature in the downlink power signal, and it's really exciting.
Don Sweetenham is a member of the radio science team and was kind enough to talk with us as the occultation was in progress. There were some very tense moments at the start.
Well, I think we started out a little shaky, but boy, we picked up now, and the recorders are going fine. We're getting the data. We're seeing the signatures. We were a little bit worried whether we'd see things, and they're there. So we're really excited. Obviously, here we go. We got another one.
All this is exciting for you guys, but tell us lay people, what are we learning from this?
Well, we're going to learn about just exactly where the rings are about Uranus. We're going to learn how big the rings are, the size of the particles in the rings. We're going to learn about the atmosphere. We're going to actually find out what the temperature is down in the atmosphere, what the pressure is, whether it's, well, we know it's very cold. We're going to know exactly how cold it is.
From JPL's radio science team, I'm David Sparks.
And now Len Tyler of the radio science team has joined me in the Blue Room. Len, it's been an exciting couple of days, particularly with that passage behind Uranus and the occultation. What sort of results do you have so far?
Well, the results are just beginning to come in. In some ways, we sort of follow behind the rest of the project in terms of when we are in the timeline. So we're just now beginning to receive and get well into the process of analyzing our data, but we have some preliminary results on
ring particle sizes. We're beginning to make good progress on the inversion of the atmospheric occultation data. And we're working on the gravity field of Uranus using the tracking data. So there's three main areas in which we are involved.
Okay, and these are the stations that are involved in this whole operation here on Earth, huh?
Well, the other 10 Voyager investigations all have experiments that are bolted to the spacecraft and carried into space. But our instrument is on the ground, and in the case of this observation, it was located in the Australian Capital Territory at a place called Tidbinbilla. This is a picture of the antennas. I should mention there was also an antenna at Parkes near Tidbinbilla, 100 or 200 kilometers to the north, that was also used.
And this is a diagram of the way in which the beam goes through the interesting things around Uranus. It's aimed back toward Earth, which is, see a little bit more of that. The beam is aimed down toward Earth, and as the spacecraft goes by, it illuminates various portions of the...
Yes, well, that's the other part of our instrument is the spacecraft itself, and specifically the spacecraft telecommunication system. We use the radio transmitters on the spacecraft as a source of energy, which is used to probe first the rings, then the atmosphere, then finally rings again of Uranus.
And this is a diagram of the amount of how the power would change as it flies behind.
Yes, if you were looking from the Earth, you would see Voyager flying from right to left behind Uranus along this track, and the red circle with the blue dot represents the size of the radio beam at each instant in time.
And here's the way the beam actually circles around.
Yes, for the
look at it.
For the atmospheric part of the occultation, the beam, even though the spacecraft is directly behind the planet, the radio beam follows a refractive path through the atmosphere to the Earth.
And that is the signal going through the atmosphere that then gives us some understanding of the nature and the part of the atmosphere.
It gives us a very sensitive probe of the atmosphere based on the same effect we see at sunset, where the rays of the sun in the Earth's atmosphere are bent.
Thank you very much, man. Okay. For all the scientists gathered here at JPL, these are exciting moments as the pictures and other data continue to come down from Voyager. There are also challenging moments as we study the information and analyze it. Seeing Uranus as we are now is one thing. Getting Voyager 2 there was another. That task was equally remarkable and challenging. Dr. Don Gray is our navigation team chief, and George Fenneman talked with him about that feat.
Don, you brought the spacecraft from Earth to Jupiter, to Saturn, and Uranus. My question is, how in the world do you do that? Because it's getting there. I mean, it's doing it. How?
It's an interesting problem because Uranus is a unique challenge for navigation. It's the most difficult navigation one we've ever faced. First of all, we're coming in on it like a flat disk. It looks like a bullseye. And that means all the optical pictures that we take are just seeing a flat plate. They don't see any depth, and so they're not able to determine when we're going to get there. And it's the same idea with our radio data. We're coming in extremely rapidly, about 10 miles every second. And we've come in, that rapidly, and now, of course, we're by the encounter. But that means that our radio data, too, did not sense the gravity field of the planet until very late in the encounter. A week before the encounter, we didn't know to the nearest minute when we'd be there. Now that we've passed the encounter, we know to the nearest second.
It boggles my mind, because I have trouble, finding the off-ramp on the freeway to get here today. How do you do that, though? What do you do to make it work?
Yes, the accuracy with which we do this encounter is more like taking a dart, throwing it here in Los Angeles, and hitting a fly in New York City. So it's extremely accurate. And we use a combination of radio data and optical data. The radio data are sent up from the Earth, and then the spacecraft turns right back around and sends it back to us. So we can see the Doppler shift in that radio data, just like you would a train coming toward you, the whistle sounds higher in pitch and then goes on by you. But, we're so far away that it takes the radio signal 5.5 hours just to go out to the spacecraft and back. And now it's winter time on the spacecraft, just as it is here. And that means the length of the day is shorter. So a typical tracking pass from one of our big antennas in the northern hemisphere is only about 8 hours. And we lose 5.5 of that just for the radio data to get there and back. Very limited in the amount of data that we can get, and we really have to make the best use of it.
How many people are responsible for navigating a shot like this?
Well, it depends on how wide a net you want to. We have 3 people who are the overall navigation strategists, with a 4th expert thrown in for good measure. Then we have about 4 people who are specialists in optical data, and then several more of us who, after we've estimated what orbit we're on, try to determine how best to get on the one we want to be on. You know, it's like we just missed the ramp. Now, how do we best get to Uranus?
But you did it, and it's marvelous. And I don't understand quite how it is done, but thank goodness you're here.
It's an exciting thing. We have a mature team. Some of us have been together since before launch.
Oh.
We've been building a championship team for 8 years now. And not only that, you know, it's kind of like there's an excitement because it's like being on Magellan's crew or Christopher Columbus' crew. We're part of the group that's doing this. And you know, when our grandchildren come and ask us, what did you do? You can say, I was part of exploring the outer reaches of the solar system.
And I can say, I talked to him, you know. Don, it's been a pleasure.
Thank you,
I'm
George.
George Fenneman.
Getting there is only half the fun. Studying that strange planet is the other half. And one of those who's having so much fun is Ken Behannon of NASA's Goddard Space Flight Center. Ken is a member of the Magnetic Field Investigation. He's with me now. And Ken, your instrument has turned up some extremely different measurements than what we anticipated.
Yes, I must say that we were not only surprised but elated because we literally did not know what to expect when we came into Uranus. And so the first indication that there was a strong magnetic field, to say the least, made us all excited and very happy. And then to go on and see that it's a very unusual field was another part of it that provided additional excitement.
I guess one of the most surprising things was the way the axis of the main magnetic dipole is arranged.
Yes, if you look down, if this was in a vacuum, if Uranus was in a vacuum and you had a simple bar magnet there, it would have this kind of configuration, and with the rotation axis going this way, sort of in the direction of the sun, the magnetic axis is oriented at 55 degrees to that axis, and that's much larger than anything else seen in any other axis orientation seen in the solar system, and has substantial implications not only for the total magnetic environment around Uranus, but for the interior structure, which I'm sure people would be working on in the next few years.
That seems to be so much. Our own magnetic axis on the Earth is, of course, tilted a little bit.
Yes, it's only about 10 degrees. Now, as I said, this is like in a vacuum. If you have this put now in its actual environment with the solar wind coming in, the actual flow, a wind of solar particles, ionized protons, electrons coming in at supersonic speeds, this highly distorts this environment, and one gets the kind of configuration. This is sort of an Earth-type magnetosphere, but we have this kind of magnetosphere, but with greater tilt, with the rotation axis also in this direction rather than in this direction as at Earth. So where at Earth, this cones around like this, as the magnetic axis goes around the rotation axis. At Uranus, we're getting a coning like this as we're going around the magnetic axis, and this has a great effect on this tail region, magnetic tail region, whereas you can see magnetic lines of force that come out of one pole have a polarity away from the planet, and in the other part of the tail, as they're coming into the other pole, they have the opposite polarity. In between this, there is a sheet or slab of energized particles called the plasma sheet. And we're seeing that on Uranus, but whereas on the Earth, this sheet, as the pole, magnetic pole, cones around the rotation axis, this sheet wobbles like this in the tail, or with the axis going down the tail. On Uranus, it's actually going to be going around like this. So it's very different, and we've seen 3 crosses through this, and we're just now starting to look at the data. Unfortunately, we didn't stay in the tail any longer than that. At 7 o'clock this morning, Greenwich time, we went out through the boundary of the tail, and we're now on our way
away from the planet and the magnetosphere, but we have plenty of data to provide us with additional excitement and pleasure over the next few months.
And this, of course, also means that the various trapped radiation that accompanies a magnetic field is going to be all swinging around. And
yes, there's going. It's a completely unique planet, and that's a wonderful way to sort of cap off this part of a long mission. And of course, we still have Neptune to go, but I think Uranus is providing us with things beyond our expectations. A great deal of excitement.
Well, thank you very much for joining us. Sometimes with our technology advanced so far, we tend to lose sight of the enormity of a mission such as this. For instance, Voyager 2 has been on the road, so to speak, for 8.5 years. 8.5 years traveling at speeds averaging 40,000 miles an hour or so. To put that in perspective, well, do you remember what you were doing in 1977, the year Voyager 2 began this journey? David Sparks recalls what some people were doing.
Let's return to the year 1977. The year Voyager 2 was launched from Cape Canaveral aboard a mighty Titan rocket. It left behind a world that desperately needed a lift of its own, a positive frontier. And as it broke the sky, the promise of such an era was born. In January of 1977, Jimmy Carter, dressed in a three-piece suit, became the 39th President of the United States as he took the oath of office with his vice presidential running mate, Walter Mondale. As the Voyager 2 mission was given birth, 1977 brought death for a pioneer of space, Dr. Werner von Braun. The silver screen lost Joan Crawford, Bing Crosby, Freddie Prinze, Groucho Marx, and his brother Gummo. And gum chewers worldwide lost one of their favorite sons. Philip K. Wrigley passed away. A 10-year moratorium on the death penalty was lifted when convicted killer Gary Gilmore was executed. And in an ultimate irony, Eli Lilly, king of drugs, died. And Elvis Presley, king of rock and roll, died of drugs. In the entertainment news, the Academy Award for Best Picture went to Annie Hall. Incidentally, Star Wars came in second in the voting. We all witnessed Roots, Alex Haley's television miniseries, and Gone with the Wind was shown on network television for the very first time. In the news were such world figures as Anwar Sadat, still alive, calling Muammar Gaddafi that very strange person. Indira Gandhi was still with us and was defeated in a national election for India's lower house of parliament. The Shah of Iran was still in power. While Voyager 2 was breaking away from Earth's gravitational pull, Mother Earth showed a macabre reticence to let go her bond. A total of 581 persons died as a result of the world's worst aviation crash when two Boeing 747s collided in the Canary Islands. The son of Sam Killer was caught, G. Gordon Liddy was granted early parole, H.R. Haldeman and John Mitchell were jailed, and Dr. Martin Luther King's killer, James Earl Ray, escaped. Patty Hearst was placed on probation. In 1977, saccharin was banned, and the Marshall Tucker Band had a gold album. And finally, in sports, the Yankees beat the Dodgers in the World Series, and the Oakland Raiders won their first ever Super Bowl against the Minnesota Vikings right here in Pasadena in the Rose Bowl. I'm David Sparks.
A little bit like the Super Bowl. That gives you an idea of how long Voyager has been on its journey. Began that journey in 1977, the year all those events took place. Ed Stone, the Voyager project scientist, has joined us again. Ed, let's talk a moment about the events that took place today and try to put them in some sort of context with the whole Voyager, Uranus, at least the Uranus portion of the mission. There's a lot happened today, but we've dwelt pretty much on the photographs of Miranda, which are so spectacular, you can't avoid doing that, and then that great picture of the material coming through the rings. But what about the rest of the experiments? We're filled with particle experiments and radio signals coming out?
That's right. Well, we did discover radio signals about a week ago now, and we're in the process of analyzing those, especially as we got behind the planet. Part of the difficulty that the fields and particles experimenters have had is they're just now getting their data from the time that the spacecraft was in occultation. It came in just this afternoon, and the second part of it comes in tomorrow morning. So I think we'll begin to see their story in more detail. There is one interesting thing that's already turned up, though, is that with the cosmic ray instrument, it was possible to look at the particles trapped in this very peculiar magnetic field that's been discussed. Once the orientation of the magnetic field was properly taken into account, it was very clear that the moons in orbit around Uranus have absorbed significant quantities of the energetic particles. And
would that affect their surface appearance?
That could affect their surface appearance, exactly. There are enough protons there that if there is methane on the surface, it would have changed the methane to a black material. The other interesting thing is we penetrated just inside of Miranda's orbit in the magnetic sense, and in there we found a very intense radiation environment, which we just barely nicked, and then we moved back out again. And so, in fact, we have not penetrated the most intense part of the Uranian magnetosphere. It remains yet to be discovered.
And this was significantly larger than just outside Miranda?
Yes, that's right. There was a distinct change in the intensity as we crossed the magnetic field that was associated with Miranda's orbit. The intensity started increasing quite dramatically, reached a peak, and then we moved back out away from the planet, and the intensity went back down again.
As if Miranda's orbit was some sort of a barrier.
That's right, exactly. That Miranda had absorbed the particles were produced inside, near the planet, diffuse out toward outward, and then they run into Miranda, and Miranda essentially absorbs them.
What about the radio signals that Dr. Scarf picks up and has made such beautiful records of, the sound of Saturn, the sound of... Is he getting data here?
Yes, in fact,
of Uranus?
he had some very interesting sounds from the ring plane crossing, just as at Saturn. What he recorded was were all the small dust particles hitting the spacecraft, and that generates electrical signal. And he heard these electrical signals, and for a period of about, as I recall, it amounted to a distance of about 2,000 kilometers.
The other radio signals that we heard as we came in, that gave us our first hint that there was a magnetic field there. I presume we're still picking those up.
Yes, we're still picking them up, although we're still waiting for this data, which has just been played back. We hope that we can use the radio signals, though, to look for a periodicity so that we can, for the first time, determine what the period of the planet is. You see, we have measured the winds, and we know that they take about 16 hours or so to circulate around the planet. But we don't know how rapidly the interior of the planet is rotating. That's where the magnetic field is generated, and if we can somehow measure the rate at which the magnetic field is rotating, we can, for the first time, know how rapidly the planet is rotating.
We've also, of course, with the UV instrument, been looking for any signs of air glow or aurora. What's come out from that so far?
Well, there was this discovery of this new phenomena called electroglow, which is neither an aurora nor an air glow. Aurora is caused by particles coming out of the magnetotail or the magnetosphere and incident on the atmosphere causing it to glow.
Northern lights.
Northern lights. The air glow is just sunlight causing the atmosphere to glow. In this case, we have a combination of the two, where you need sunlight, but you also need energetic electrons, and the two together give this new phenomenon.
Very good. Thank you, Ed. We'll see you tomorrow, and I think we'll have another update from you, and I appreciate everything you've been able to tell us. And this sort of sums it up for today. We're waiting now for tomorrow, and still more excitement. We hope you'll be with us again when we look at more of the Voyager spacecraft's encounter with the planet Uranus. Good night. I'm Al Higgs.
Encounter with Uranus. You've no doubt seen its television images of our seventh planet's small cratered moons. Those images are transmitted back to Earth across more than 1 billion miles of space, and many of them images will eventually become maps, aiding investigations into the nature and origin of the solar system, including the Earth. All of the basic maps of other planet surfaces produced in the United States are made right here in Arizona at the Astrogeology branch of the U.S. Geological Survey in Flagstaff. And as can be seen in the following report, there is more to mapping another planet than simply copying spacecraft images.
Here at the Astrogeology branch of the U.S. Geological Survey in Flagstaff, Arizona, artists and cartographers turn spacecraft images of other planets into maps. These maps do a lot more than show how to get from one place to another. They show the mountains and valleys, the geology, and even the chemistry of other planets. All this information is implied in the spacecraft images, but before it can be used, it must be interpreted by skilled map makers.
And so if you go to the planet and you take pictures of it, but you don't map it, you don't look at the pictures, and you don't interpret them, or you don't try to understand, then there's really no sense.
You need the maps for planning and for scientific inquiry. Because if we see dunes on Mars, are they just randomly placed? Or if we plot them carefully on maps, we'll say, the wind for most of the year blew in this direction at this speed. Or we say, a river runs in this direction because the slopes are that way. That's what maps do for you. They're shorthand. They're notation that you can make to put scientific observations together so they make more of a picture.
Mapping begins with images made by television cameras carried by spacecraft. If you enlarge one of these images, you'll see that it's made up of thousands of tiny squares called picture elements, or pixels. Each pixel falls somewhere between black and white on a scale of gray tones. Its particular shade of gray can be given a number. And so an image is turned into a string of numbers.
And it is that string that's transmitted back to the Earth. And the advantage of that is you can transmit a string of numbers over tremendous distances.
The numbers can be reconstituted into pictures on a television screen or directly onto film by a computer-driven machine called a film writer. But an unprocessed image is still not ready to use.
There are distortions, and the distortions are caused by the magnetic field, for example, of Jupiter, which is very significant, and they are also caused by a drift in the sensitivity of the television camera, which varies throughout the image, and it also varies with time. It's a very complicated relationship.
The image is computer processed to remove these distortions, and then processed again to give it the main thing that makes a map different from a photograph. A regular, mathematically describable system of relating a round planet to a flat surface. A projection, in other words. This is done in the famous Mercator map projection. Now, the images can be joined together into a photomosaic.
The most obvious way to make a mosaic is to take a pair of scissors and a stack of pictures and a pot of glue and cut out the pictures in the right place and glue them down next to each other so they fit. Anyone who tries this will very quickly discover the more pictures you put down, the harder it is to make them fit, so there is quite an act to it. We then turn that base over to the airbrusher, who will use the base for a geometric control. We'll trace everything that he or she can see on the base, and then they will take a collection of images that have been processed and enhanced in various ways, or taken from different parts that weren't included in the mosaic, and they'll use those to refine all of the surface detail that they can possibly pick up on the surface. We have a group of people who are trained to look at all kinds of images and to interpret those in terms of what that landform actually looks like. What does the surface really look like, regardless of how it's illuminated, regardless of the atmospheric haze or the weather. And these people are able to look at 1, 2, 50, or 100 pictures of the same area to draw a mental image of the surface they're seeing. They're not copying the photograph, they're making a painting of the image that they see in their minds. And to put this in the correct map location, and so that everybody else can see the same image they saw.
The completed maps go to NASA's mission planners, among others.
Right now, for example, we're working for the science team for the Galileo mission to Jupiter, which will take more and more highly detailed pictures of both Jupiter and the satellites of Jupiter than were taken by Voyager. So we are making maps that they will use to plan their mission data gathering sequences.
And by using colors, we can show maybe 30 different data sets on top of each other by shading, by colors, by lines, and you can compress an enormous amount of material into an easily comprehensible form.
Some of the data added to the basic maps will show the geology of Jupiter's satellites.
And that program's coming along fine. The map I have is a map of Io, a certain quadrangle on Io, called the Ruwa-Patera quadrangle, that I'm mapping with Dave Scott and Ron Greeley. And it's all volcanic terrain, and it's a completely different kind of map than I've ever done before. I've done a map of the Moon, Mercury, Mars, and now Io. And this is the most difficult because it's all volcanic material, which has got lots of gases on the surface. There's active volcanics going on. It was a totally different challenge, which I enjoyed greatly. And I think from my results, I've already found some very interesting relationships that I can relate the geology to models of the thermal evolution of Io that people have been proposing.
Without maps, we cannot organize what we see on other planets. With them, things fall into place and make sense. Patterns emerge. Relationships become clear. It isn't just the map that does this. It's the relationship between the map, the process by which it's made, the purposes for which it's used, and the minds of the people who make it and use it.
So it's a very powerful analytical tool.
At midnight tonight, Channel 8 will broadcast the fourth of 5 one-hour programs.
This photo is of the first new Uranian satellite discovered by Voyager 2, called 1985 U1. It's a small, irregular sphere about 90 miles across. This is the NASA Science Report.
NASA's Science Report is a special summary of events leading to the Voyager 2 spacecraft's encounter with the planet Uranus. The programs originate live from the facilities of the Jet Propulsion Laboratory in Pasadena, California, and are authorized by the National Aeronautics and Space Administration. The NASA Science Report, Voyager 2 at Uranus, is one of a series of public information programs designed to keep the public informed of space exploration.
Hello, I'm Al Hibbs at the Jet Propulsion Laboratory, and we're watching NASA's Voyager 2 as it continues its encounter with the planet Uranus. We're looking over the shoulders of Voyager scientists as they receive new information on Uranus and analyze it in its original form. We'll be discussing its significance, the mission's scientific goals, and what this encounter can teach us about our world and the universe. At 5 o'clock this evening, Pacific Standard Time, Voyager is 2,544,000 miles beyond Uranus, and it's traveling away from it at 33,172 miles an hour on its way to Neptune, the last planet it will visit, and it won't get to Neptune until 1989. Let's take a look at some of the more exciting photos that the scientists have been analyzing over the last 24 hours. This, for example, a backlighted picture of the dust in the ring plane. We've been taking many pictures of this, but it took a 90-second exposure to bring out this material. Tiny motes of dust with the sunlight shining through them from behind. These are the images of stars smeared across the picture because it was a 90-second exposure to bring out those. And then that amazing moon, Miranda, which has across its surface features that we've never seen on any other satellite or planet. Large geologic formations indicating something is happening beneath the surface, but not expected on anything quite so small. And this, another moon, Titania, which was filtered by a computer to bring out very sharp edges, emphasizing the sharp detail and sort of blurring out the gray in between. Notice how much detail there is on the surface and compare it then with this one. Umbriel, very bland, and yet they're both part of the same satellite system. And this Ariel, down near its lower, from this point of view, lower portion, canyons, where it appears that something is slumped down into crevices left perhaps by the surface pulling apart. And another view of Ariel, the complete one now, with similar canyons up at the top of the picture. All of these formations quite unexpected in bodies that were so small as this. With me now is Dr. Ed Stone, the Voyager project scientist. And Ed, let's talk about what's been happening today.
Well, as you've already pointed out, there have been some new images of the satellite surfaces, which again are quite interesting and are telling us something which we don't yet understand. In addition, this morning it was reported, we managed to report the first measure of a planetary rotation period, or at least what we think may well be the planetary rotation period, a period of about 17 hours.
That was from the magnetic field data, or?
Actually, we determined that by observing that the radio emissions coming from the planet had a certain periodicity to them, and that periodicity was about 17 hours.
And these radio messages are stimulated by the magnetic
That's
field.
right. Presumably they're tied to the magnetic field, which is then generated interior to the planet. Once we have a planetary rotation period, then one can determine how rapidly the winds are blowing, because we already knew that the clouds circulate the planet once every 16¼ hours or so. That tells us that the winds in that atmosphere are something like 100 to 200 miles per hour.
Compared to whatever it is responsible for the magnetic field.
Yes, compared to some deeper portion of the planet. That and the winds are blowing the same direction as the planet is rotating, which is somewhat of a surprise. We had really, I think, most had expected that because the poles were expected to be hotter than the equator, that the winds would be in fact blowing the other direction. Well, we also learned today that in fact the poles are not hotter than the equator. As far as we can tell, the planet to first order is the same temperature at all latitudes, although it is about 2 degrees colder at a small region at mid-latitudes. Again, quite a surprise.
But the cold spot then is neither the equator nor the pole, but sort of in between.
In between, that's right. Sort
temperate zone, so
yes.
to speak.
And I think the best way to describe it is that we just don't understand exactly how all of this is happening, but it's very clear that the atmosphere is not exactly what most of us expected it would be.
And we had, speaking of the magnetic field, this very odd offset of the axis of the magnetic field, the axis spin, must mean some rather weird behavior of the magnetic tail of this planet as it blows back from the solar wind.
Yes, we would expect that since if this is the sun, the magnetic field will wobble like this, that the whole magnetic tail will rotate like a sausage, if you like, with a 17-hour period. It's unlike anything we've seen before.
What about some of the, I've just been stepping through some of the pictures of the moon, but I didn't say too much about them. What about those?
Well, I think that the Umbriel is really an interesting moon in the sense that its surface seems to be the oldest surface in the system. It has very large impact craters, and it's a fairly soft-looking object. On the other hand, the other moons seem to have sharper and smaller impact craters, as though there has been the old craters have been erased, if you like, by a more recent bombardment. So we have, again, a variety of ages in the system.
We've been waiting for some time for the radio occultation data to come back. What does that show us?
Well, one interesting thing is it's shown us that, at least in the Epsilon ring, the particles there are likely to be larger than a meter across. This should be contrasted to Saturn, where most of the particles were a few centimeters. It is really a remarkably different kind of ring. These are particles which are this large rather than this large, dominating the rings.
Very surprising. Where are the little particles? I mean, these things must bump together occasionally, and there must be little particles, not those.
Well, there are some small particles, and that's what the backlighted image of the rings that you just showed show us, that there are some, but there are relatively few of these small particles. Something is cleaning them out of the system as rapidly as they're produced.
And the ultraviolet, what are the early results from that one?
Well, on the dark side, we indeed found aurora. That is northern lights. There is a hot spot somewhat near what we believe is the magnetic pole. We're not sure exactly where it is yet because we have to map it out more carefully. But there's no question there is indeed a classical aurora on the night side.
Ed, thank you very much for that fast review, and we'll talk again later. The centerpiece of this encounter is, of course, the Voyager spacecraft. Let's go live now to Von Karman Auditorium to get a checkup on the health of Voyager 2.
And I'm Bill Griffith here in Von Karman with Project Manager Dick Laser. Dick, you've started each of the press briefings each day with the statement that Voyager so far is working perfectly.
But I didn't say anything today, right? That's because it continues. I really didn't have anything to say. It's going great.
Do you do periodic physical examinations, if you will, electronically, periodically?
We're continuously monitoring the engineering data coming from the spacecraft, engineering data that describes the state of each of the subsystems and the instruments on the spacecraft. Then in addition, when we have time, and this will probably be after we get through the encounter time period, we do very specific tests to check out the memory of the computers and things like that.
During the Saturn encounter, you had that problem with the platform, jammed and so forth. We can go over to it now.
Why don't we do that? It's easiest.
How's it working now?
It's working perfectly. It did everything that we asked it to, and to the best of our knowledge, until we do the next one of the tests on this. As far as we know, it is in perfect health.
You corrected the problem.
That's right.
Let me talk a little bit about how it works, and then we can talk about how we corrected it. This is what we call the scan platform, this whole device right here. And basically, it's sort of like an upside-down tripod, and all the instruments mounted on it can be swiveled around in azimuth or up and down in elevation. And basically, what happened when we were just about at the time we were crossing the ring plane at Saturn was that the device that turns this in the azimuth direction, which is way up in that part of the spacecraft, it's sort of like a gear train. It got stuck. And we went several days without any pictures, any data at all from the science instruments on the stand platform until we kind of pushed it back to where it ought to be, and we got several nice parting shots of the planet.
This has been crucial, especially for Uranus, because you've had to take, and by the way, these are the two cameras here that have taken those fabulous photos, not only of the planet, but of Miranda and so forth.
The wide angle and the narrow angle, sort of like a telephoto and a super telephoto.
So if you hadn't had the platform okay for this encounter, you couldn't have gotten those high-resolution photos.
We would have been hurting. We had an alternate technique which involved rolling the whole spacecraft, more or less taking this whole spacecraft and spinning it around on the floor here. But that would not have yielded as good a mission as the one we just had.
Quickly, if you can, explain to us, I mean, the spacecraft was going 45,000 miles an hour when it passed by Miranda, for example.
Right.
And you had to correct the movement of the camera to get those high-resolution photos. How'd you do it?
Well, basically, I think you're talking about the target motion compensation, and what we did was point at a target. I'll kind of point out toward the audience there. And then, if that target was moving, what we did was literally move the whole spacecraft. If we move the platform, it's kind of jerky, but we can move the whole spacecraft just at the right rate, very gradually, very slowly, and in fact, track that target so that it isn't moving in the field of view, just the background.
And I think it was you that said it in a press briefing that it's like shooting a race car that goes by
exactly.
in
Same
moonlight
principle.
at 45,000.
Same principle.
Yeah. Thank you, Dick.
Sure.
Dick Laser, the project manager for Voyager. I'm Bill Griffith in Von Karman Auditorium.
We've talked a lot about pictures from Voyager, and we've shown you many of them, but Voyager can also see in the invisible regions of the spectrum, and one of Voyager's instruments measures infrared radiation from the planet and its satellites. And here now to talk about that experiment is Dr. Rudy Honnell from NASA's Goddard Space Flight Center. Rudy, what does the iris measure, and what have you learned from it? I believe it can do something about actually determining what the chemical nature of the atmosphere is, yeah?
That is correct. This picture here shows, so to speak, our raw material we work with. It shows the spectrum, which is the infrared color, if you wish. As a function, we call it wave number, but those are just different colors.
And this is the spectrum of the light that's being given off just because the gas sort of glows in the infrared.
Well, it's not so much a glow, it's a thermal emission. Every body emits a certain amount of heat, and we analyze the heat radiation. You see here two curves. One is a black one, which is a measured one, and this is our raw material we work from. Incidentally superimposed, you have here a red curve, which is a theoretical fit for 10% helium in the atmosphere.
So that particular concept, just that 10% fraction, is the best fit to what you've seen in the study?
Well, it seems to be the best fit. Of course, there's some uncertainty. To include an uncertainty, we quote really a 15% as an upper limit of the helium concentration.
Since you're measuring the thermal emission of the gases, you can also make a temperature map.
That's quite correct. And may I show the next slide here? What we have plotted here is the temperature in degrees Kelvin on the lower part versus atmospheric pressure. 1 atmosphere, that is the pressure of our own atmosphere on Earth. Of course, the atmosphere of Uranus is much, much deeper.
This is really only the top layer of Uranus.
This is only the top layer we can measure. And you see that it's not too different from our own atmosphere. It has temperature minimum, and then above that, the temperatures rise again into stratosphere.
So our temperature does the same thing. A tropopause between the troposphere and the stratosphere.
That's correct.
This is coldest spot.
Except our atmosphere is much, much warmer than that one here.
That's about 350 below 0 Fahrenheit.
Right. What we have shown here are 2 temperature profiles. One for the dark pole, which is appropriately the dark curve, and the other one is for the light pole, which is the dashed red curve. What is so surprising to us is that those temperatures are almost identical. Also, the one pole has been exposed now for many years to the sun, the other one not.
About 20 years. It's been
That's
absorbing
right.
sunlight, and the other's been radiating away heat.
But
yet
it
here they are.
shows that that atmosphere is so massive that it has such a long thermal time constant that it hasn't cooled off. And a certain amount of dynamic forces may play a role in that too.
You've also measured the temperature, I think, in more detail between the equator and pole.
That's right. Here's a temperature, the mean temperature at about 800 millibars, which is shown here versus latitude. 0 latitude corresponds to the equator, and 90 degrees latitude is the sunlit pole in this case. And here we show again temperatures, and it's only 1 degree Kelvin, which is about 1.8 degrees Fahrenheit, is from one tick mark to the next. So as a whole, the planet is extremely uniform, and
It's
it does
surprising
not...
that the coolest spot is sort of midway up.
That's right. The coolest spot is so between 20 and 30 or 35 degrees latitude. This is incidentally the latitude where the television people see those methane clouds.
That's fascinating, Rudy.
Everything seems...
Yeah. As more astounding results continue to pour earthward from Voyager 2, members of the news media from around the world hang on to nearly every word and event. We were there for this morning's news briefing.
Today's press briefing proved that the more Voyager scientists find out about Uranus, the less they actually know about it. For example, Uranus is a very cold planet with temperatures as low as minus 350 degrees Fahrenheit. But surprisingly, it turns out the pole on the dark side of the planet is warmer than the pole facing the sun. Dr. Andy Ingersoll said the temperature differences between the poles, therefore, are not caused by the sun, but by some unknown internal process. Some of the results of the radio occultation of Uranus are starting to come in. That's the process where Voyager took a silhouette of the planet by sending radio signals back to Earth around the planet and through the rings. The early data confirmed for investigator Len Tyler that the very dark rings are made of very large particles.
What we can say is that the particles are certainly larger than about 4 centimeters, which is about what this actually is, I think, if we were to measure it. And I suspect that they are much larger than the one over here on the right.
Larry Soderblom released this photograph of the rings with the sun as a backlight, and it showed very small particles between the rings.
But there's many, many other features in here. The estimated densities are such that it would be impossible. Well, it would be difficult to see these from the Earth. They're very, very diffuse, sparse material, perhaps only a few 10,000 individual particles, a micron in size per square centimeter. Very, very low density.
Soderblom also released a high-resolution photo of the mystery satellite, Umbriel, the darkest in the Uranian system, and as expected, it showed a distinctively featureless body.
If you look here, you'll notice that the surface of Umbriel is composed of overlapping large, mostly large craters in the neighborhood of 1 to 200 kilometers typical diameter. The crater-like form up here, this white donut, we suspect is in the floor of a crater about 150 kilometers in diameter. You also see a bright patch here that may be more of this bright material. Now, this bright material itself is only about 30% brighter than average Umbriel. So Umbriel is about a 15% albedo. This might be 25%, so still it's fairly dark material.
Project scientist Ed Stone said the latest data released only served to deepen the mystery of Uranus.
Each day it just gets better. We certainly didn't expect to find, I think most didn't expect to find winds which were prograde, that is, blowing the same direction as the planet rotates, yet that's exactly what we seem to have. I don't think many expected that there would be such a equilibration of the temperature between the equator and the pole, although that was always recognized as a possibility, but I don't think anyone really seriously considered that as what we would see. But now that we've seen it, we still don't understand it, and I think that also should have come through clearly this morning. We certainly didn't expect to find a dark polar stratosphere that was warmer than the sunlit side. And I don't know of anyone that suggested that we would find rings which were mainly meter-sized and larger particles, when at Saturn all the rings were mainly centimeter and smaller size. I mean, it's the difference between this. And again, it's just an indication that the Uranian system, as with the satellites, is just totally different than anything we've seen before.
With today's press briefing, I'm Bill Griffith.
One of the truly fascinating experiments aboard Voyager listens for waves that propagate through clouds of plasma, and those waves vibrate at audio frequencies. Don Gurnett of the University of Iowa is a member of the plasma wave team, and he's with me here to discuss it. How does it work, first of all?
Well, the plasma wave experiment is intended to measure waves and radio emissions in plasmas. This instrument uses two long antennas, which are about 30 feet long. They're shown schematically over here in this diagram. These are the two antennas. Now, although the instrument was designed to study plasma waves, it turns out that it's also...
This is a wave like a pressure wave in air? Is a sound wave in air or something like that?
Sort of like a sound wave in air, only it's in this ionized gas that we call plasma. It turns out that this type of instrument is also very effective for detecting small dust particles that hit the spacecraft. The Voyager spacecraft, as it moves through the ring plane, is moving at a very high velocity. And when a dust particle hits the side of the spacecraft here, it essentially explodes. A small part, of course, if it were too big, it would go through and damage the spacecraft. So these have to be, we know they have to be very tiny particles. When the dust particle hits the spacecraft, it just explodes and instantly vaporizes and creates a very hot pulse of plasma, which expands and emits electrons, which are detected by the antenna.
So the particle doesn't have to hit the antenna directly. It hits the spacecraft, and then the plasma does it to the antenna.
We first detected this effect at Saturn, and our analysis is that we're detecting impacts on the spacecraft and not on the antenna. Well, we can detect these effects two ways. We have an intensity measurement in our instrument.
Well, why don't we hear what it sounds like? Okay. That's what I'm really interested in. Yeah.
Well, let me describe how we detect the voltage difference between the antennas, and that voltage difference is amplified and transmitted back to the ground, and then we can convert it to an audio tape. And this is a recording of as we flew through the ring plane at Saturn, and what you should listen for is, it's like hail hitting a roof. Okay. A whole bunch of impacts, and I think when you listen to the tape, you can hear this effect. Hear all the static. The static consists of a whole series of impulses. Each impulse represents a small particle hitting the spacecraft, which we're detecting.
It wasn't designed for it.
It wasn't designed to do that, but it turns out the spacecraft has a very large area, and it's very effective at detecting such small particles.
Thank you, Don. I think you know we've been very busy here at JPL during Voyager's encounter with Uranus. We're not alone. For space scientists at many other facilities in the United States, around the world, busy on other missions planned for this year. Karen Long tells us what's involved.
Space exploration will never be the same after 1986. Major activities are planned every other month this year, prompting NASA to call this the Year of Space Science. We'll see new voyages to outer planets, international comet watching in space, never-before-seen views of the sun, space shuttle innovations, even a giant orbiting telescope to bring the universe home. This month's highlight, Voyager 2's encounter with Uranus. Now, scientists say they'll learn more in 10 hours than they've known in 200 years since the planet's discovery. In early March, an armada of spacecraft from Russia, Japan, and Western Europe will chase after Halley's Comet. The European Space Agency's Giotto will dare to fly within 500 kilometers. That's just 300 miles from Halley's. It's risking total destruction from the comet's magnetic field and particles. NASA will also participate in the international Halley's effort by tracking the 5 foreign satellites from its deep space network, a series of antennas based at strategic locations around the world. We talked with JPL Chief Scientist Dr. Mustafa Shaheen about the joint project. Why is it the Russians, Japanese, and Europeans not tracking their own Halley's missions? Why is JPL involved?
JPL is involved in it. From their point of view, we already have the best network of ground antennas to make observations of any point in space at any time we want. For the Russians to duplicate this at this time, it would probably be expensive. They have to go into treaties with many countries in order to have their antennas spread all over the globe. Likewise with the Europeans, I believe they feel that it is to their best interest, economically speaking, okay, for the cost of their missions, to rely on us. We hope that this will be a precedent, okay, by which joint investigations, joint scientific investigations of planets will be done in the same manner.
NASA is planning some limited Halley's observations of its own, using existing spacecraft from other projects. According to Dr. Shaheen, NASA originally planned to conduct a major effort at Halley's, but budget restrictions prevailed.
The decision on selecting a mission at that time did not go in favor of a Comet Halley, and we this year have missed the chance of having a dedicated mission to Comet Halley.
What will we miss in the way of information?
We have expertise, longer term experience in observations from space. We have made some of the most impressive, most descriptive images of planets. We could have made images like this of a comet like Comet Halley. The Europeans, the Russians are going to have the capability to obtain images, but we believe that our ability, our experience would have played an important role in making our images by far more meaningful,
in other
more
words,
descriptive.
We could have put up a better craft, perhaps, and one that would take better pictures.
Yes, and also one that would have taken also different types of measurements that are not included on the European or the Russian spacecraft.
If all goes as planned in May, NASA will launch Galileo, one of the most sophisticated spacecraft ever constructed. Its mission? To fly to Jupiter and orbit the turbulent gas giant for nearly 2 years of close-range scientific study. When Galileo reaches Jupiter, it will drop this capsule-like probe down into the atmosphere. It'll pick up measurements on composition and temperatures and send them back to Galileo. And it may only be a matter of a few hours before the probe ceases to function. 5 days before Galileo's launch, the International Solar Polar Mission will get underway. Now known as Ulysses, the craft is designed to orbit the sun's poles, vast territory that has never been seen before. Just launching Ulysses and Galileo will be history-making events. It will be the first time any interplanetary craft is launched from space shuttles. During late summer, the long-awaited Hubble Space Telescope will be shuttled into orbit above the Earth. Scientists say it's a major turning point for space observation. They'll soon be able to look 7 times deeper into space, beyond restrictions of the Earth's atmosphere. Stars and galaxies some 12 billion light years away will soon be within our visual reach. Needless to say, 1986 will open a new era of space exploration. This year, as we celebrate the 10th anniversary of Viking's landing on Mars, we might also brace ourselves for discoveries promised in the coming decade. At Pasadena's Jet Propulsion Laboratory, I'm Karen Long.
I've been saying that Voyager can see in the invisible, and we've talked to Rudy Honnell, who studies infrared. Now I've been joined by Lyle Broadfoot, who studies Uranus in the ultraviolet, just the other end of the visible light from the infrared. Welcome, Lyle, and tell us what you found so far. One thing we announced today is quite exciting. The long-sought aurora has shown itself.
Yes, we had to move to the back of the planet before we were able to detect the aurora. It's we detected in a sequence that looks like this. That's the projection of our slit on the planet.
So that's a piece of the planet you actually sense with your ultraviolet sensor. Right?
And we scanned out this type of an array, and just as we moved up this far side, we found a very large signal in in our instrument. And
Is that where it's expected? Is that near one of the poles? Where it
yes,
comes through
that's close to one of the poles.
Magnetic pole.
The magnetic pole. And we expect to be able to position the pole by using the ultraviolet.
How could you tell it was the aurora and not just... Well, you found so many different things in the ultraviolet, so many types of hydrogen glow, one sort or another. How did you know this was different?
Well, the spectrum is quite distinctive. On the dark side, we have this. We have the overlay here of the aurora. The auroral spectrum looks like this one, the green line. And on the day side, we have this other very large intensity from the Lyman alpha, and then again the overlay of the H2 emission. There's very characteristic differences in the spectrum.
Well, I was going to say the aurora is caused, I guess, by charged particles coming down the magnetic field line.
That's right. The charged particles penetrate deep into the atmosphere and lose their energy by driving off electrons. Those electrons multiply and start to radiate. The energy then comes back out as radiation.
I see. And the other kinds of glows are stimulated by what? By sunlight, or?
Well, mostly by sunlight. On the day side, we usually see what we call day glow, which is a process by which the atmosphere absorbs the sunlight and then re-radiates it. In most cases, we know exactly what kind of process causes the radiation. This large signal in the center here that is saturated is actually an emission called Lyman alpha. It's the line of atomic hydrogen. It is backscattering the signal from the sun. It absorbs the photon from the sun and radiates it.
And you see this quite often in a big cloud around the planet.
That's right.
Hydrogen that's evaporating off, presumably from the planet. Now
that's right. A corona. We call that the corona, and around the Earth we call it the geocorona.
So the Earth has the same thing around it.
Yes, Earth has. Hydrogen is the lightest of the materials. And therefore, if anything escapes from the planet, you can be sure that it's going to be hydrogen.
And that's
first.
what you found here.
That's what we found.
Well, thank you very much.
Thank you.
The distance from Earth to Uranus, 2 billion miles, is staggering. To travel an equal distance, you would have to cross the United States coast to coast 666,666 times. I don't know who figured out that number, but it's a beauty. Rich Terrell is a Voyager scientist who's good at putting that distance in perspective another way, and David Sparks talked with him.
Rich, everything that we hear about the Voyager 2 expedition and the planet Uranus is so filled with astronomical numbers, if you'll forgive the term. Would you regale us with some of your more down-to-earth analogies?
Let's try to put it into a perspective that at least we can visualize sitting here, and maybe everybody else can visualize as well. For instance, if the Earth, we can shrink the entire Earth down to the size of a head of a pin, okay? The Earth-Moon system turns out to be about 1 inch apart, and the speed of light at this scale turns out to be about 1 inch per second, okay? So we can imagine the Earth-Moon system. The sun would be about the size of a grapefruit, and it'd be about 45 feet away. And if you can imagine looking at a grapefruit from about 45 feet away, it's about the same size as the sun looks like to us in the sky. Now, Uranus turns out to be about 4 times larger than the head of a pin, so let's say it's a green pea, okay? And that pea is located now about 900 feet away, or 3 lengths of a football field away. So if you can imagine looking at a pea from 900 feet away, that's about what Uranus would look like from the ground, and that's what we have to contend with our ground-based telescopes. Okay, well, Voyager is going to fly past this pea at about 9 million miles away. It's about 4 feet away from the pea. It'll fly within a half an inch of this pea. So you can imagine the incredible view it's going to get of the Uranian system compared to the view we get from here. Another thing is that Voyager has to be flown at a very, very precise trajectory. It has to fly through a very, very small area of space and time at Uranus in order to bend its trajectory to fly onto Neptune. And Neptune is another pea. It's about twice as far away, about 6 football fields away. Now, the area that Voyager must fly through, 900 feet away from the head of a pin, is about the same area as that's swept out by about 1/10 the area of the eye of a needle.
Okay, thus far we have the Voyager going past Uranus and then on to Neptune, but once it leaves our solar system, can you give us more of your analogies about what we can expect it to meet?
Okay, well, actually, Voyager will be sort of on its own for the next 40 or so thousand years before it encounters anything else. And after about that time, it'll be encountering some of the nearby stars. Now, on the same kind of time scale, the nearest star to us is of course, the Alpha Centauri system. And that's another grapefruit, size of the sun. Only on this same length scale, it's about 2,000 miles away. So from here in Pasadena, the next star would be a grapefruit in Chicago. So that gives you the kind of scale of the vast emptiness of interstellar space.
The normal, usual way for a scientist to work is to gather his data, take it away, analyze it, think about it for what might be considered a long time, writes a paper on the results, the paper's published. It's thoughtful, considerate process. But these space missions drawing worldwide attention, we've become used to asking for what Voyager investigators call instant science. We found Brad Smith, the Voyager imaging team leader, and asked him about that.
It's called instant science.
Excuse me. Do you know exactly right now the diameter of the satellite? Could you confirm the diameters of the satellite? Because there was a kind of uncertainty whether they were... do you have the exact diameters of the satellites right now? I mean, precisely? Are they precisely known?
Could you explain a little bit about the apparent elongation of 1985 U1? Is that largely defect? Is that an artifact, rather, or is that something that likens it to some asteroid-type shape?
If you took the Epsilon ring and rolled it up into one big gunky snowball, how would the size of that snowball compare to one of these new small satellites? It is a phenomenon that seems to be unique to the American space program, and more specifically to planetary encounters. What happens is NASA scientists give their instant analysis of data just received from space after only a few hours, and in some cases only a few minutes analysis of that data. The leaders of the various Voyager teams have been in the scientific hot seat during the Uranus encounter, and no one has been in a hotter seat than imaging team leader Brad Smith. His team has had to make heads or tails of photographs of a very dark planet.
That's the problem. We are expected to do instant science. Tomorrow morning, we will have to stand up before 200 members of the press and tell what's in this image. And emotionally, we're sort of caught up between feeling absolutely elated that we have some remarkable science here to talk about, and feeling like complete idiots because we can't even identify the rings that we were talking about just a few days ago.
But Smith emphasizes that he is by no means complaining about having to perform instant science.
The American public pays for the space program. It's a very expensive program. They're putting out their dollars. They want to know what they're getting for their money, and that's reasonable, and we understand that. And the problems that we ourselves get into in trying to do this instant science is a result of the American public's interest in the space program, and that is gratifying. The fact that they really want to know is gratifying. But the hope is that somehow or other it will be communicated through the media that we are working under conditions that we don't normally work under. And if we make a mistake occasionally, that will be forgiven.
And while Uranus has produced some of the best science data of the Voyager mission, it has certainly been the toughest to analyze instantly because of its distance from Earth and the low light levels. This ring image is a good example. It arrived yesterday afternoon, showing the planet's ring system from the other side of the planet with the sun as a backlight. And by last night, Smith and his team still didn't know exactly what they were looking at. At today's press briefing, Smith had a bit more to say about that ring system.
The particles that are seen in the backlit image are small. We're talking about a micron or a few tens of microns.
Instant science. I'm Bill Griffith.
The magnetic field experiment aboard Voyager has been providing some of the most unusual and unexpected results we've received from Uranus. Now, here to talk with us about those results is Jack Connerny of NASA's Goddard Space Flight Center. Welcome, Jack, and tell us about these rather strange discoveries.
Well, I'd have to say that in terms of the space scientists that deal with magnetic fields and charged particles and all the exotic little creatures in the magnetosphere, the most disturbing or surprising result was the tilt of the magnetic field with respect to the rotation axis.
Certainly unexpected.
Well, if you look at the chart here, the direction to the sun is shown here. And of course, the spacecraft entered the magnetosphere basically along the planet sun line. We were all expecting a magnetic field, if any, to be aligned essentially with the rotation axis.
Like all the rest of the planets, more or less.
Like most of the, or all the planets that we've seen so far. And it's not just the planets we've seen and measured the field in. For instance, for the Earth, there's millions of years of records of the magnetic history of the Earth. And in all those millions of years, the pole, the magnetic pole, has stayed close to the geographic pole, the spin axis.
It's reversed sometimes, but it's never gone one way.
It reverses, it flips one way, it flips the other, but it prefers that state where it's near the axis. And when we started studying the outer planets, we found Jupiter with a similar tilt, about 10 degrees, just like the Earth. And we expected Saturn to have the same sort of field, and we were all amazed at that time to find that Saturn's magnetic field was perfectly aligned with the rotation axis.
No tilt at all.
No tilt at all. And that runs contrary to expectations, of course, and it runs contrary to a lot of theoretical work that people have done for a number of years. So when we came to Uranus, we expected again to find a magnetic field close to the pole or even aligned with the pole. And the surprise was that it's almost an oblique rotator. It's almost, well, the pole is closer to the equator than it is to the pole. It's hard to accept, it really is. For instance, let me put it in real terms. If this magnetic field was what the Earth had, we'd have one pole, say, in Los Angeles, and the other pole would be in the Indian Ocean off Madagascar.
You used the word oblique rotator. This sounds like there is a name for such a phenomenon. Are there other bodies in the world that have such behavior?
It is. In astrophysics, they have a lot of exotic phenomena that they deal with. Neutron stars, pulsars, and in their theoretical work to try to understand radio emissions and even light pulses from pulsars, they have as a part of their conceptual framework an oblique rotator, a construct, a gizmo.
So there is a
with
theoretical
a
notion
field.
that this does exist.
It's a notion.
But far away in stars, and certainly this isn't anything like a star. This hasn't gone through a stellar history.
No.
And yet that must, supposedly, has something to do with the motion of a conducting core somewhere in Uranus, which is moving around in a way that's totally separate from the rotation.
Yes, if you have a magnetic field, basically it means you need currents. And planets apparently like to generate such currents with motions of fluid in the deep interior. That's another problem for dynamo theories, this particular magnetic field, because it was thought by most people that you need convective, very heavy convective motion, like heating a pan of water, and you need to heat something in order to induce that convective motion. Now, apparently Uranus has a very, very low heat flux. They haven't measured it. It's so low to date. And so the question then arises, what provides the energy input to generate the magnetic field,
and what
especially an
and
exotic
what provides
one like
this kind of motion?
Right.
Jack, thank you very much. It's one thing to send a spacecraft to a distant planet like Uranus. It's quite a different thing to get useful scientific information back. The key to that feat is the Deep Space Network, the antenna complexes that girdle the globe and converse with the spacecraft. Karen Long is in the DSN's control center.
This is the control center for the worldwide Deep Space Network, which tracks, commands, and gets data from spacecraft across the length and breadth of the solar system. One antenna complex is located at Goldstone, California, in the Mojave Desert northeast of Los Angeles. The antennas that track Voyager are 112 feet in diameter and 210 feet in diameter. A second complex is located at Tidbinbilla near Canberra, Australia. Here, in addition to our own giant antennas, we're borrowing the great 210-foot Parkes radio telescope, 200 miles northwest of Tidbinbilla. Now, that's because Australia had the best view of Voyager and Uranus at the height of the encounter. The third antenna complex is at Robledo, Spain, about 40 miles west of Madrid. 2 Spanish antennas are part of Voyager's network. So, while any part of the world is sleeping, somewhere a deep space network antenna is tracking Voyager 2 on its journey across the solar system. I'm Karen Long.
Now by Hal Mazursky of the U.S. Geological Survey, who was a member of Voyager's imaging team. And Hal, we've heard that Uranus may have been knocked on its side by some huge cosmic impact. Have you seen any evidence in any of the pictures, of the moons, or anything about the moons that might give a clue as to whether or not that happened?
Well, the moons have been very active in the past, and they're quite varied from inside to out of their distance from Uranus. But I don't think we see anything of that very early event. That probably happened in the very early history, and we think that the satellites are relatively young products. And what we see now are stages in the evolution, the geological evolution of the satellites.
Mm-hmm.
We think we're seeing much later stages, but those are exciting enough. And that brings up another thought, that is, now we've seen some spectacular pictures of Miranda.
Indeed so.
We've put them together in a mosaic, we've enhanced them, and we see some real differences from place to place. Now we get to the place where we have to synthesize some ideas, get some kind of consensus on what might explain these. And that brings us into an idea that was promulgated by one of the early geologists, and that is, don't seize on an idea and try to prove it no matter what. What you do is that's called a working prejudice. Instead, we try to devise various explanations and use multiple working hypotheses. You say, if this happened, then this is the geologic history. And you try to construct each of these, then match them with the evidence that we see in pictures and we'll get from the compositional measurements. Let's look at a couple of pictures of Miranda, for example.
This one is one that greatly intrigued me.
Well, I'd like to start with this.
Right?
Well, the reason for it is that there are these rounded off circles with bright and dark streaks. Now we have another kind of feature that looks like this. This is near the terminator, so you don't just see the bright and dark. As a matter of fact, it's very hard to see the bright and dark. What it looks like are ridges and valleys, again laid out in this squared off or circled off square pattern.
A little different, but both appearance and color are different here to here.
Yes, but now the question is the first one, bright and dark circles, and this one, the same kind of feature. We've had a considerable debate. Then it gets even more interesting because here's the end of that circle, and we have the chevron.
I mean, right down here, that's the end of that scene we're just looking at.
But the chevron has quite a different outline. It has quite rectilinear, angular, bright and dark things, and here we can see beautiful faults that bound those, and another fault that cuts across these. And then finally, tracing that fault off into the distance, here's the chevron again, and the small faults go off, and here we see an enormous fault scarp that we've measured.
That's a cliff.
That's a cliff that is probably at least 5 kilometers high. We don't have a very good number on it yet, but that has some striations on it. And that might mean the faulting has polished that and grooved that surface. So we know the sense of movement, and we see the topography offset. Now we have to put all of these ideas into something that fits together. And here's where our either working prejudice or multiple working hypotheses come in. And we've had a very interesting discussion this afternoon with, of course, universal agreement instantly on everyone's part.
I can imagine how much agreement there's been on everyone's part. Well, it's a baffling set of pictures.
Well, what really is interesting is you try to work on, say, an impact origin for all of them, and you fill stuff in. You have stacked layers That was one of the early ideas coming in, that it's a volcanic thing with layers coming this way, that it's a great hunk that's been buried and is now re-exposed in the crust. But the fascinating thing is to say, take that idea and pursue it. Test it against the crater counts, the way the faults are, early, late, does it make sense? And that's where the real fun in our game comes in. The exciting part is planning it, carrying it out, getting the pictures down on the ground. Then the real battle starts of geologic ideas.
Wouldn't it be excellent if you could actually get out there and walk around on the surface, collect a few samples?
Yes.
That's right. This is the real challenge, to have to do it this way.
Yes, but you get very cold feet.
Thank you, Hal. As we've told you throughout this series of programs, Uranus is a fascinating planet. It's a discoverer, and the times in which he lived were fascinating, too.
Uranus was the first planet in our solar system to be discovered with a telescope. Because of its distance from Earth, it cannot be seen by the naked eye, so it was unknown to ancient astronomers. It was discovered by William Herschel back in 1781. He's a German musician who had settled in the English town of Bath, the cultural center of Great Britain at that time. Herschel was also an amateur astronomer, and with his brother Alex and sister Caroline, he built a 7-foot telescope he planned to use to catalog stars.
In the March of 1781, during this cataloguing of the sky, Herschel discovered one object which he saw on 3 consecutive nights. On the 13th of March, he was convinced it was the same object. That object he thought was a comet, and he wrote up the paper which Watson delivered to the Royal Society later that year, and they then became sure that it wasn't in fact a comet, but in fact a planet.
The planet was called Herschel as late as 1850. Then Britain's Astronomer Royal officially named it Uranus. In Greek mythology, Uranus was Saturn's father and Jupiter's grandfather. But Herschel's career took off as a result of his discovery. He was elected a fellow in the Royal Society and appointed King George's private astronomer. Dr. Gary Hunt is the Voyager team's unofficial historian on Uranus. He owns some of Caroline Herschel's private diaries. And according to him, Uranus's discoverer was a rather colorful man.
Herschel's life really was more than that pure discovery. He did a great deal more in astronomy, but had a very close relationship with the monarch, the king, and pretty through his connections with then Sir William Watson, as he later became. The king became heard of Herschel. Remember, this is the period in the late 18th century. George III had been preoccupied by other things at that time, namely a little battle with the colonial states in America, and that had taken his mind away from astronomy. But George III was interested to learn about Herschel. He invited him to London, and Herschel came with his 7-foot telescope and star catalogues under his arm and presented them to the king. And the king said, well, if you're only an amateur, you will see how good you are. And the Astronomer Royal took the telescope and tested it at Greenwich and was convinced it was better than the professionals. So there we have, originally a musician who had developed telescope systems better than the professionals, who then had the royal patronage. And the king, at that time, gave him a salary of a civil pension of £200 a year, when the Astronomer Royal, the leading professional, was getting a mere £300 a year. Now, of course, salaries of that sort, when you get it from the monarch, they have little caveats, things you have to do for the king. And one thing he had to do was to entertain the king at court, to show them the night sky when the need arose. Herschel, in fact, by now had moved from Bath to the small town of Datchet and ultimately settled in Slough, which is one of the places you fly over when you fly to Heathrow. And one particular night when Herschel had to go to the castle at Windsor to entertain the prince and princesses and the king and the queen himself, it was a typical evening in London, the London area, covered in cloud, therefore not a star in the sky. Herschel was worried. He had a salary of £200 a year to protect, so he rigged up a little model of Saturn, which in fact hid outside the windows, and therefore when the royalty looked through the telescope, they could see Saturn dangling there quite truly, and they were quite pleased, actually delighted, that they could see so much in the solar system. So his career was tremendous. He carried on his music throughout all of this, and I think he really has laid a tremendous foundation to not only the discovery of Uranus, but also in developing astronomy itself.
From the interactive room, I'm Bill Griffith.
Good story. Well, we're nearing the end of another day of tremendous excitement for the scientists and engineers of the Voyager project. And here again to help us put all this into some sort of perspective is Dr. Ed Stone, the project scientist. Ed, we've we're still getting data down. Recorded data is still coming in now, so we haven't even got all the data, much less many of the answers. What's going to be coming up next?
Well, I think that we should be able to take the photopolarimeter stellar occultation of the rings and convert it into an image, very much like we did at Saturn. And some of those images, I think, will really show some quite amazing structure in the rings, some of which Lonnie Lane has already indicated with some of the early looks at it.
So with his graphs.
With his graphs. I think we can now make some images, and that, I hope, will be done by tomorrow. I think in the area of the atmosphere, the radio science occultation, the scientists there are working very hard to analyze the pressure versus temperature profile, and in turn interpret that in terms of how much helium there is in the atmosphere, this whole question of what is the helium abundance.
Yeah.
And I think that is something which is now basically ready to be analyzed.
And is it likely also they'll be able to determine whether or not there are other things in the atmosphere that we can't quite see as clearly as we would like to?
With this particular investigation, they really only get what's called the mean molecular weight.
Right.
They can only tell what the average weight is, and so if there's something besides helium there, they won't be able to directly determine it.
But they'll notice that something is there that doesn't quite come out in the models.
That's exactly
Okay.
right.
Good.
Then I think we also will be able to say something more about the hazes in the atmosphere. There have been a number of reports from the imaging team about hazes, but I think with a photopolarimeter, which does very accurate measurements, we may be able to say something about the global distribution of the hazes in the atmosphere.
The photopolarimeter, we're talking about working over just over the rings and getting all the structure there, but it's one big job is just the atmosphere itself.
The atmosphere itself. And then in the magnetosphere, the data has finally come in, and today and tonight the scientists are working on it. I think we'll come up with a fairly comprehensive view of the distribution of plasma in the magnetic field. I think we'll have some of our first observations of what the plasma waves were like when the spacecraft was in the sun's shadow behind Uranus, and also what the high-energy particles are like that are trapped in that magnetosphere. So that's also something which is being worked on. And finally, in the case of the satellites, one missing piece of information has been what is their mass, so that we know what their density is, whether they're mainly water ice, half rock and ice, or mainly rock. I hope we'll have that answer by tomorrow as well.
How do we determine that?
Well, there are several ways to determine it. The way which I think may be the quickest is to take the optical navigation data where the orbits of the satellites were very carefully measured, and the satellites interact with each other and perturb the orbits, their orbits. And by measuring very accurately how they interact with each other, one can determine their masses.
It's a very tiny interaction.
A very tiny effect.
Accurate measurements.
That's right.
The spacecraft has now gone out of the tail, of the magnetic tail of Uranus, is it not?
Yes, we have left the magnetosphere after having been in it for, I think it was, I've forgotten how many hours it was, but enough time so that I think we hope that we can have seen this tail rotate several times. And that should help us map out the structure, because from the standpoint of the magnetic field, you can think rather than the magnetic field of rotating as if the spacecraft is making a spiral through the magnetic field.
You draw it from the magnetic field's point of view.
Yes, right. And so you get to map the magnetic field at an increasing radius and distance.
But we're still, even though we're outside of the magnetosphere, we're still getting signals that indicate what's happening inside of it.
We're still receiving radio signals, and those will be very important because the period which has been reported was reported from radio measurements before encounter. After encounter, we'll be able to monitor those same signals and add to the length of the database we have so that we can determine a much more accurate radio period for the planet.
And that radio period and magnetic period hopefully are the same period.
That's right.
The atmospheric features, has anything shown up when we flew by the planet and looked up close, the closest approach, looking down on the planet? Anything come up from that?
Just a few of the same clouds or plumes which were discovered earlier. It turns out the atmosphere, the clouds, the real clouds evidently are so deep in the atmosphere that they just normally aren't visible.
Well, now we're 3.5 days beyond Uranus and still receiving data, and we will tomorrow, Ed. Thank you very much for telling us about it. Tonight, all the scientists will be working hard, extra hard, to put together as cohesive a picture as possible of Uranus, its rings, satellites, entire environment out there, 2 billion miles from the sun. We'll be back tomorrow to bring you more of that picture. Until then, we'll stand down. I'm Al Hibbs.